Okay. Do you see, everybody sees the right thing? Yeah, just nodding would be good. Okay, perfect. So, all right. So welcome here to this course, which is a course related to driven. So the idea of driven, just to inform people that might not know and to remind people that will know, is to put together different strong research partners that are located, in our case, at INRIA in France, the team of Stéphane Cotin, at Limerick in Ireland, team of Paul Weaver and the whole Composite Center, and the ISIS in Texas, which is the, in fact, it has now a different name. It's called the Odin Institute, and they are one of the world leaders in the field of computational mechanics. And the idea is that these partners will try to support the development of the University of Luxembourg in certain directions, academically, but also from the administration point of research. So to do that, we have set up different streams of work, which are related to biomechanics on the one hand with INRIA, composite materials and multi-scale methods on the other hand with Limerick, and fundamentals of data-driven methods with both INRIA and Texas. And so today we talk about one small component of this whole picture, which has to do with a topic which came up during the many discussions that we had locally in Luxembourg before, as we say in French jargon, in the previous world, and in the next world, we'll see what happens. But in the previous world, we had meetings here in Luxembourg, and we discussed what topics could be of interest. And isogeometric analysis came up as one of the top topics, and also it didn't need to be voted up using some very fancy software called Speak Up. It could be voted on face-to-face in a room, and that was several years ago now. And so that's why today we have this course. What I've done is I could teach this for basically 2 to 3 weeks easily. So I have material for several dozens of hours, probably 60 hours easily. And of course, we don't have 60 hours because people are busy doing other things. And I have selected topics which I believe are fundamental and that without which you cannot understand what's going on in the literature. So my goal really has been to give you the basic building blocks such that then you can learn on your own. Also, in parallel to that, we have a piece of software which is downloadable on computational mechanics open source on the SourceForge. So the name of the site, it will be given later, but if you want to take a look at it, it's computational mechanics OS at SourceForge, and you can there download an isogeometric code which does everything, more or less, not everything, but most of the things that I will show you today and the next days. Okay, so let's go. All right, so by definition, some of you will probably believe that you already know all this, and probably you do, and it's fine. I'm, learning myself every day, not only in that discipline, but generally speaking. So there may be some topics that you think are kind of useless, or maybe too superficially treated, or maybe treated too much in depth. So this is unavoidable because the audience is quite varied. So I cannot possibly do an in-depth course about how to implement Nurbs, because 90% of the room would be disinterested. So I have to give you an overview first, such that then you can tell me which topics you'd like me to cover more. And so that's what I'm going to do. And then I'll try to adapt as much as I can. So I have the afternoons to try to catch up with what you asked me to cover in the next days, and that's what I'll do. So don't be shy. If there are things that you like for me to talk about, there are many things I don't know, so I'll just tell you I don't know. But if I do know, or I can point you to papers that can help you, then I'll do that. And that's my goal. So the idea at the end of this course, my aim is that you know where to find information about IGA, and that at least you have a basic understanding of the key terminology, so that when you read papers, you're not completely lost trying to figure out what people are talking about. And therefore, the introduction is the following. And now this is okay, wonderful. Okay, great. Okay, so basically, yeah, there are many people that took care of working on this. Actually, one of them, and maybe others that I haven't seen, is here, Hussein Rappel. Thank you for joining. It's really kind to take time to listen to IGA. So there are many topics: multi-scale, advanced discretization, error estimation, biomechanics, and multiphysics. So I listed a few of the people that were involved, but as you can see, there are many people. So it's already about probably 30 or 40. And I would like to start with a topic which I know is not of interest to Limerick in particular, but that gives a very good idea of what we try to do in IGA. So we are trying in IGA to remove the problem related to meshing. And what you see here is a needle being inserted in an organ. And the idea is that as the needle is going to be inserted locally around the needle, you're going to have the need for local refinement unavoidably, because the needle is a very sharp object. The organ is very large. You cannot mesh the organ fully to the scale of the needle, because that would mean having billions of elements, which basically is not doable, especially if you want to deal with a real-time simulation, which is the case here. So IGA, like any other methods that are trying to help make meshing easier or avoid meshing, is going to constantly deal with talking about, what is a mesh? Why do we have a mesh? What's the purpose? What are the drawbacks? Can we generate it? Is the mesh high quality? Is it too low quality? What type of elements do we have? What is the order of the element? Can we refine? Can we not refine? When? How? Do we have locking? And so on. So these questions will come around continuously in the talk. Okay. So in that particular case, you see, this is work that's done by INRIA, one of our twinning partners. So when you insert a needle by Stéphane Cotin, to be very precise. So you see the red arrow is it's a needle that's being inserted in a liver. This is a liver, which you see the gray thing. And when you do that in a real liver, when you need to locally, as I was saying, refine the mesh, because simply the needle is far too fine. So as the needle gets inserted, the mesh is refined locally around the needle. And it's not refined anywhere else, it's only refined locally. And that's useful, because if you want to help the person inserting the needle to insert the needle at the right place and exert the right torque or the right force in order to reach the target, which is somewhere at the back here, then you need to know how the needle will deform, how the body will deform. You see the breathing pattern here, which goes up and down. And you see these elements here, these little bricks that look like Legos. These things are the finite elements. And in that case, the finite elements are simple finite elements. They are based on Lagrangian shape functions. Lagrangian shape functions are shape functions which are 1 at the node and 0 everywhere else. I will, by the way, assume that you have some knowledge of finite elements so that I can use certain terminology. If you do not have that knowledge, please let me know in the chat so that I can help you get to grips with that. But I would recommend the book by Thomas Hughes, which is a blue book called Finite Element Methods for Statics and Dynamics. It's now in the collection Dover, almost for free. It's extremely cheap. And it's really, in my opinion, the best book to start, because it has everything from the mathematical theory to the very advanced topics. So if you don't understand some of the terms, then that book is really perfect. because it's not too advanced, not too mathematical, but has a little bit of a mathematical flavor, which is going to help anybody feel confident. Now I'm going to set the scene. I'm going to tell you where we start. And I already make here on that slide many assumptions. So I will assume that we have a continuous problem. So what does that mean? If you have a piece of material that you are deforming, like a piece of composite material, we will consider this problem, this piece of material, as a continuum material. So in order to describe that properly, you would need a continuum mechanics course, which takes about 30 hours. But this, and which I'm teaching currently at the university. But this continuous problem assumes that you can boil down material points to one point, and that everything happens as if a material point was infinitesimal. You have now an infinite number of these material points in a domain. And you assume that you can compute stresses, you can compute tensors, so first order tensors like vectors, displacements, second order tensors like strains and stresses, fourth order tensors like constitutive tensors. You can compute them locally at a point. And these things are pointwise defined. They are not defined as at a particle, like you would do in discrete elements, where each little ball has a finite size in discrete elements. Here they have an infinitesimally small size. And you derive the equations of motion by taking a representative volume, so a control volume, making it shrink to zero, looking at the balance of forces. For example, you write that the divergence of the stress should be balanced by the external forces. So you have a flux of external and internal forces and body forces, which is compensated by the divergence of the stress. So it means that whatever changes in terms of stresses is only due, in that assumption, to changes in forces, which are applied externally or internally, like body forces that are volumetric forces. So that is what I mean by the continuous problem. So typically, so I take here an example where things are complicated geometrically. But of course, here, instead of having a tongue and a brain, I could have an airplane with complicated geometries, and that would be also fine, you know. Later, or at some point, we can have another course on multi-scale methods where we can talk about how to deal with problems such as composite materials, where you cannot deal with all the layers one by one, because there are simply too many layers. So that's the continuous problem. First of all, you need a geometry. So that's the first problem. I need to write an equation. Once you have that equation, that is called a mathematical model. This is what I was referring to with the divergence of stresses. Here we have two parts of the stress. We have one part, which is the passive stress, standard Cauchy stress, for example. And again, here, there are 2 or 3 one semester lectures behind how to choose the stress measure and how to choose the strain measure. Lars Bakes in the Legato team is teaching that as well this year. And this is not something which is trivial at all. I have to be I cannot talk about this, but this is something already in itself that requires a lot of understanding. So here I just show you an example to illustrate what can be this stress. So here we have a passive material and a muscular activation term. So these two terms are here because they are serving different purposes. And the stress is the total stress. Let's, for example, say the Cauchy stress. And here you have the epsilon, which is the infinitesimally small strain tensor, which is the symmetric gradient of the displacements. So 1/2 of the dyadic product of the Nabla operator with U plus the transpose of Nabla dyadic product with U, and that gives you the small strain. Yeah? Essentially, if it's in 1D, it's the derivative of the displacement, right? So now you have the mathematical model. So here, lots of assumptions come, right? So for example, you have to say, okay, I want to assume there is a passive part and an active part. For example, if you had active materials, which are the very new and fancy materials that are trying to mimic muscles, then you would have an activation stress, which comes from, which is due to strain, and which comes from the electric impulse going through the wires inside this active material. Okay, so you make a lot of assumptions. You may assume small strains, large strains, isotropic materials. So you could assume that things are homogeneous or heterogeneous, and so on. So that is where the assumptions come in. At some point, you need to have some sort of geometry as well, because if you solve for problems, then you need to know what domain you solve it on, and that is related to the boundary. And the boundary conditions are some of the most difficult things that you have to model in real life. So be it in composites or be it in aerospace, in space, in biomechanics, in any domain, the boundary conditions are probably the hardest things to actually identify, along perhaps with the material model and their parameters. Okay, once you have the mathematical model, you end up with a discrete problem. So this is what we're going to talk about today. So all these very interesting points about the continuous problem, the mathematical model, and so on, we don't talk about today at all. What we talk about today is only the discrete problem. So this is, I just want to really emphasize that this is a very small part of the whole process in a certain way. So if you're an engineer in a company, or if you're a researcher, same thing, you want to tackle a problem. The first difficult part is actually to figure out how you write this problem down in terms of mathematical modeling. And that is the hard thing. And I know in the audience that there are people that are actually trying to work on trying to figure out what is the mathematical model from experiments. So if you see experiments, you try to figure out what the mathematical model is that could replicate these experiments. And you try to do that perhaps using statistical inference or artificial neural networks or Bayesian inference or other things. Yeah? And I know that someone in the audience is doing this. So, and he's smiling now. So this is a very nice topic to work on, because in that case, you don't know what the model is that is going to govern what you see in real life. And this is a tough problem. And we're not talking about this. We're going to talk only assuming we know the problem, and now we want to discretize that problem, which in a certain way can be argued is much simpler, because you know how many centuries and have gone into finding mathematical models for things. You know, like we had Newton that worked like crazy to come up with a model, and then Einstein came and said that it's valid only in certain circumstances and generally not valid. At least let's say it's not sufficient. So it takes ages and ages to come up with mathematical models, but once you have them, you can be relatively safe. But I'd like to emphasize this because most of the time when something doesn't work in a simulation, it's not necessarily because the discrete problem is wrong, but it could be that your model is making assumptions which are not valid. And we forget that too often, simply because it's much harder to come up with a new model than it is to come up with a new discrete problem. So a lot of work is going on in the literature on this discretization, and much less work, in my opinion, is going on in the mathematical modeling and the continuous problem finding or identification, or singling out the continuous problem. And this is something, you know, for young researchers that want to select a field of work. I would say that working in the top two blocks here is probably going to have quite some impact. Okay, but today we talk only about the bottom part, and that's called the discrete problem. So now we assume that someone came with an image, and that could be an image of a composite, by the way. It doesn't need to be a brain. I know I have brains everywhere because I'm a bit obsessed with biomechanics, but this is just you know, professional deformation. Let's put it this way. Nothing to do with small strains. And so you have here a discrete problem, and that's not so easy. So if you see on the left-hand side, you have a hexahedral mesh. Okay, so hexahedra are cuboids. They are like parallelepipeds. Well, that was tough. And on the right-hand side, you have mesh-free discretizations. So these discretizations are nothing else but sets of points. So the points are just sprinkled over the surface and in the interior, and you solve without having a structured mesh. So that sentence is very heavy with past observations, because we had 30 years, I would say, easily, of research, or no, much more than this. Monaghan, 1977, so yeah, 60, yeah, almost 60 years. Yeah, maybe 60 years, over 60 years of work going on in the field of mesh-free methods, starting with SPH, smooth particle hydrodynamics. After that, coming up with mesh-free methods that looked more like finite elements, the left-hand side thing. And the idea of a mesh has been indirectly debated for decades, really. And these decades led to discussions such as what do we call a mesh? Because a lot of methods were called meshless or mesh-free. For example, the element-free Galerkin methods of Ted Velichko in 1994, 1995, and with Fleming. These papers talk about a so-called method which would not have a mesh, and they use points which are connected to each other by their neighbors. And that could lead to another course which would take about 30 hours to actually talk about that properly. And well, the conclusion was really that most so-called mesh-free methods were not really mesh-free because they had to rely on a mesh for certain operations. And the operations are the following. The first is that you need to cover the geometry of the domain. This is what you do with a mesh. So this is what you see on the left-hand side or at the top. The top is a tongue, and you see these little triangles that are covering the shape of this tongue. And they are non-overlapping, but they create a partition of the domain, meaning that you can cover the whole domain with them. And if you were interested in a bit of math, you know that the paving problem is a very difficult problem. So if you have an arbitrary surface even, and you try to pave it with certain shapes, this is not a given that you're going to be able to pave this surface with certain shapes. Certain shapes cannot be paved. You need certain specifications on the geometry of the pavement. And then you're going to be able to cover the shape. But it's not the general statement. You cannot do that generally. And this is what limits the use of meshes, because if you have an arbitrary complex domain, for example, this brain here, there is at the moment no proof that you can cover it in a finite time with arbitrary shapes. So it means that it could be that you start trying to mesh it, and you could go in circles, and the algorithm would go in an infinite loop, and you could not actually finish the meshing process. And if you have done practical work on meshing in ANSYS, Abacus, IDS PLM solutions, or whatever other software you use, you're then very used to the fact that if you have very slender regions, very thin regions that are too close to very large regions, which are like kind of bulky, then the transition between these regions is not easy to get if you generate a mesh by hand. When I say by hand, I mean automatically with the software, but still by hand because you need to move things around. And so this is why people came up with these mesh-free ideas, where the hope, the grail was that you could just put some points, but you don't need to know how they are connected. They can be loosely connected. You can just find the neighbors by looking in a certain disk or a radius around yourself or bowl, and you find a center point called a star point, and then you look around the star, and if you find other stars there, then you say, okay, I'm connected to 12 stars. That means that my element now has 12 nodes, so to speak. Then I move to another point, and I see in the same radius, I now find 25 nodes. And these star points are going to be the points that I use to draw the shape functions. And these shape functions we'll talk about a lot in the course, because they are the underlying approximation of the whole problem. And this is what you see today in neural networks, which are super approximation machines that allow you to approximate almost anything with an otherwise rather simple structure. So this is the idea of the of meshing. Meshing is not easy. One, you need to work hard, and you need to work still by hand. Two, it is used in order to compute the integrals that you saw when I was writing the continuous problem. If you remember, there was an integral of the divergence of the stress. So that integral is going to be written in a weak form, typically. And for that, you will need some integration points. And so, in fact, the mesh-free methods were not so mesh-free because you needed a connectivity, but although the connectivity was loose because you were looking in these little balls, right? And you also needed to integrate the weak form because most of the mesh methods were based on weak forms. It's not the case of collocation and generalized collocation and SPH, but most of mesh methods were based on weak forms. The ones that are not, I will give you a reference article that Thibaut Jacquemin, my PhD student, wrote recently on what you can do in order to avoid having to do this numerical integration and work directly from the strong form. From the strong form means the equilibrium equations without being integrated over the domain. So you simply write at each point the equilibrium equations. So that is called collocation. These collocation methods are very versatile, but unfortunately today there is almost no mathematical analysis that can tell you a priori whether the method will converge and at which rate. And that is obviously problematic because if you are an engineer and you want to have a solution, you want to know if the method is going to converge and how. This is why Thibaut Jacquemin in my team has worked on error estimates for such methods with Oleg Davidov in Germany and with Pratik Suchte, who is now in the team here as a Numerically fellow. They have worked on trying to identify the error of the simulation a posteriori, once you have the solution. So I'll talk a lot about that later. So not about this particular problem, but about a priori and a posteriori, what that means. Consequently, you can use collocation methods. You can look at the convergence rates. You can look at the error, although you don't know the exact solution. You can compute that. And in that case, the method could be called probably truly mesh-free because you do not need a mesh at all. But still, there is still a difficulty. So it's really difficult to abstract yourself from meshes. This is why this course is interesting. And why is it so difficult? Because the question is that the position of these points, let's say that you have collocations or mesh-free methods, actually it works also for integrated methods like MLS, which are based on the weighted residual method like finite elements on the left. The problem is that if you just simply sprinkle the points everywhere, then the accuracy randomly, let's say, the accuracy is deteriorating significantly. You cannot just say, I will put points anywhere I like. So first of all, it's obvious because you see here there are very many little holes and little sulci, these high curvature areas. So in these regions, you definitely want more points because you have more geometrical definition. But far away where things are quite flat, you can do with less points. And these questions are difficult to answer. So in my team, Sofia Farina is working on the brain, which is not the brain, but one cell in the brain, which is called an astrocyte, which is extremely small compared to that thing here, but it's not simpler in terms of geometry. It's actually probably even more complicated. It looks like some giant octopus, but with dozens of branches. And she starts from images, and at some point we would like to avoid the mesh, but the problem is even there avoiding the mesh is not easy because locally you have so many complexities, and that happens in composite materials also, that you simply have to refine the mesh locally in some way. Okay, so that long introduction on the mesh was necessary because if you think about it, you look at the literature and you think historically about what led us to where we are today. We started in the 70s with Monaghan and SPH. Then people came up with weak form based mesh-free methods. That was basically Belichko, Winkham Liu with RKPM and element-free Galerkin. At the same time, Ivo Babushka came up with the partition of unity method in 1994, 1996 in the CMAME paper with Marcus Melenk. And that partition of unity method was trying to make a bridge between the mesh-free methods and the standard finite element method by enabling enrichment of the solution. So you could do partition of unity enrichment, locally put what you know about the solution inside the approximation. And then IGA came about in 2005, so which is 10 years after partition of unity methods and extended finite element methods. and probably 10 to 20, 40, depending if you suppose that SPH is a measuring method after the first, let's say, dips into mesh free. And there is a reason why the method is very successful, actually, and this is what we're going to talk about next. Until now, I've only talked about the fact that generating this mesh is complicated, and that even though you try to do without a mesh, it's not always so easy. And I've been talking in very general terms. So if one of you talks to me about crash, for example, or high velocity dynamics, my response will be completely different than if you talk to me about quasi-static loading of this brain. If you want to look at what happens if a bullet is fired for the brain, God forbid, then the problem is completely different. If you take a composite material, you want to see what happens under crash conditions or bird impact. The type of methods to use is not going to be the same as if you would like to simply look at the deformation under standard loading of the wing, let's say. So one needs to keep that into account. We wrote a paper in 2008 with Nguyen Vinh Phu on mesh-free methods, which summarizes this. It's in Mathematics and Computers in Simulations. And I will give you the link to that in case you don't know it yet. And we also wrote a paper on isogeometric analysis review and computer implementation a bit later in 2000, I believe, 15, which deals with trying to explain how IGA works and what are the links with other methods such as mesh-free. Okay, so now let's assume that we have this mesh and we solve the problem and we get a numerical solution. So that's what we have here. So that's the tongue. You have small and large displacements, and you're happy. You get your colorful rainbow, and everybody is satisfied. All right, now let's ask ourselves, what are the types of errors and, let's say, difficulties and complexities that we need to know in order to assess what we see when we get a result? This is the most important thing that as engineers or researchers you need to know. You cannot simply look at colors and tell yourself that this is necessarily sufficient. You need to learn to assess the results. So the first error level, so I talking about errors is a bit negative, but let's call it assumption maybe. The first assumption is that you take a problem, could be composite materials, and then you need, could be biomechanics, and then you need a model for that. But unfortunately, the model that you come up with is not what you would like to model. So that thing, that equation, which looks fancy, does not exactly, obviously, describe what happens in real life. And this is why smart people are working on trying to look at experiments and derive the model from the experiments. And there are very nice papers in Science on this, where they look at the double pendulum and find back the Hamiltonian just on based on looking at the oscillations of the pendulum. Just by observing with the camera, they can come back with the equations of motion by using neural networks. And this is a super cool topic. But anyway, even if we do that, at some point we'll make mistakes. Even Newton made mistakes. So not mistakes, but he couldn't know what he couldn't see. So same for us. We cannot know what we cannot see. And maybe there is something we don't know about the system. And in composites, this is very true. For example, the A380s were grounded because of many reasons, but also because of this tendency of composites to swell. So if you couldn't land in Hong Kong, for example, for too long because the wing would swell, and then you would have problems. Then there was the whole problem with fatigue, which grounded half the A380 fleet and led probably to the fact that the program was not continued, probably jointly with the fact that the airports couldn't take so many people. Growth of aircraft of airports a little bit too much when building the A380. But anyway, we cannot know everything, and this is what is encompassed in this model. So if you do fracture of composites, for example, you will say, okay, I have a cohesive law model between the different plies, But that cohesive flow model, you know almost nothing about. You can do a lot of tests to try to do debonding tests. You can do, you can put a wedge inside and try to see what is the fracture energy and the cohesion energy of that wedge, of that plies. But at the end of the day, you can do so many experiments, and at some point you will put this piece of composite somewhere in an airplane, where the conditions will have nothing to do with the conditions in which you actually did the experiment in the lab. So there are many things you don't know. Environmental conditions, temperature might change much more than you had predicted. So one way to deal with that, which I'm not talking about, but which many people in the audience work on, for example, Hussein Rappel at the Turing Institute, works on stochastics, and Bayesian inference to identify not only models, but also parameters, and try to decide what you do about these errors, so that you have a stochastic model. So following what Laplace was saying, that anything you don't know is basically encompassed inside a probability distribution. So if you don't know something, it's because it's in the probability distribution. Because if you knew everything, you could start from the beginning of time and move step by step until today, and you would know exactly how you got there, and you would know exactly where you will go in the future. But that's not the case, because a lot of the things that you are dealing with are stochastic. So this is about the material model, or the choice of the equations. And this is called the model error. And very few people are working in the model error, because this is, as I said, very complicated. The second thing is the geometry and the boundary conditions. This is, as I said before, extremely difficult to identify in general. Why? Because the geometry, if you make a piece of composite, for example, is not going to be perfectly exactly what you like. It's not a circle, it's not a sphere, it's not a cone, it's not a flat surface, it's rough, it's got tolerances that you need to take care of. It's not going to be manufactured to the micrometer scale or the nanometer scale. So, you have to deal with that. The carbon fibers, they won't be aligned at 45 degrees, but at 44.7 degrees. And the different plies will be, glued together along a certain interface, but the glue will not be constant thickness. It will be varied thickness. And all these things need to be taken into account. So boundary conditions is extremely difficult. And that will come up later in IGA, because this is a special topic for IGA. Okay, then discretization error. What is discretization error? Well, you start from a mathematical model and you move to discrete problem. And the idea is that you would like to discretize the problem. Why do you need to discretize the problem? Well, if you have, as we said, a continuous problem, you have an infinite number of points, obviously, unless you can solve it by hand, which happens if you are Timoshenko, Goodyear, and these people. So you sit down and you take the problem and you solve it by hand. If you have a circle, a disk, a cylinder, maybe some spherical geometry or some Cartesian geometry, you're going to be able to do that no problem if the equations are simple enough. In general, if you have a shape like this, even which is not so complicated, you already cannot solve by hand. So you need somehow to solve numerically. So numerically means you have a finite size computer with a finite memory. Therefore, you need to make this infinite number of points, which we had when we assumed that the problem was continuous. You need to make this problem finite. So you have to, instead of having an infinite number of these elements, now you have a finite number. But the problem is, where should I put these little material points, which are these little, these corners here? Where should I have more of them, and where should I have fewer of them? Because nothing tells me that how to choose this. I just have no idea to start with. I just solve a problem, but I don't know where I should have more refinement and where I should have less refinement. So we'll talk about that, because this is a very interesting problem, which would again take at least 30 hours to cover. So then your computer, which is a completely finite computer with a finite memory, will give you some solution, and you will have to solve that problem. You have a discrete problem. So a discrete problem is AU equals F, or KU equals F, and you want to find U. K is a big matrix, maybe 1,000,000 by 1,000,000. U is a 1,000,000 by 1 vector. F is a 1,000,000 by 1 vector. You want to invert this thing. Of course, you never invert it, but you solve it using whatever method. But whatever method, by the way, will always lead to a numerical error, meaning that your computer will do round off things, and it will, round off using 32 bits or 64 bits or whatnot, or maybe it will be a quantum computer, I don't know, but at the end of the day, you will end up with a solution which has some sort of pollution that comes from the numerics itself, from the fact that you cannot compute infinitely accurately. That's the final error. We're not talking about this. So today, we talk only about the middle thing, the discretization problem, right? That's it. The rest we don't even talk about. And that's important because in reality, if when you are someone in real life, let's say here again, I'm obsessed with computational mechanics, so you will see bleeding things all the time. So this is like a brain here, and someone is a surgeon, like surgeons with whom we are working here in Luxembourg. They need to insert needles into this and try to figure out where they should insert it in order to reach a certain target, as you see below here. But when a surgeon does this, he doesn't have in his or her mind what is the model error, what's the discretization error, what's the numerical error. What they see, these people, is what you see here, right? They see a real thing. And then let's say that you give them a simulation. That would be cool, right? Because you can tell them, okay, well, look at the beautiful colors. But the reality is here and the simulation is there. And you have in between, the total error, but you don't know how it's split. You don't know how much is in the model error, how much is in the discretization error, how much is in the numerical error. Let's forget the numerical, say that you don't make any errors there. Let's say it's very small. So you have a model and you have a discretization, and you don't know for sure what is what. You don't know what the most important error is. And that's what you need to know, because that's how you will improve your model. All right. And this is why the project Driven was actually came to life, because we, here in Luxembourg, we, with Andreas Zillian, Bernard Peters, Francesco Vitti, and the whole team of computational engineering, we thought, look, I mean, we have this model here, but we don't know what it is. And this is why we have people working in the teams on trying to identify the models directly from experiments, because we have a model, but we don't know what it is necessarily. And we have a discretization. A lot of us have worked on that a lot. But at the end of the day, we don't know when we have the total error, what is what. And that is, as an engineer, exactly what you're interested in. So if you do experiments on composite materials, which I know you do, and you look at buckling or post-buckling of composite panels, for example, then you're going to see a buckling load or post-buckling load. And your question is going to be, okay, well, I mean, I get something experimentally. How can I get that back numerically? And that's my question. Because if I can get it back numerically, it means that I'm quite confident that in real life, I'm going to be able to use that model again in other circumstances, which are not modeled in the lab physically, but somewhere else. And if it's reproductive, if I can reproduce my results, which is the first pillar of the scientific method, or if I can actually falsify these results, saying that these results are wrong, because I can prove they are wrong, like, Einstein proved that Newton was right to a certain extent, but later on, for certain big things or very fast things, he was not right anymore. Then if I can do that, I'm happy. But the problem is, for that, you need to know how the total error is split. But today, again, we don't talk about all these very fancy things. We talk about something much, let's say, self-contained, and this is the discretization error. How do we discretize a problem? And that is the point. Now, when you read papers, you very often encounter fancy words and jargon and so on. So my goal is to dispel any type of jargon, because I think jargon hides the fact that we don't know something. So the more people use fancy words, the more it means that they probably don't necessarily completely grasp what is behind these fancy words. So I would like you at least to see what is meant by what, so that when we talk later, we are on the same page and we don't need to use very fancy words. So if we ask, there are two questions that we ask when we do numerical simulation. The first is, are we solving the right problem? And this is called the model error, asking what is the model error. And the second problem is, are we solving the problem right? meaning are we solving the problem correctly? So meaning if we have the problem in hand, do we solve that precisely enough? And this is what we talk about today. The first one, are we solving the right problem, is called validation. And the second one, are we solving the problem right, is called verification. And often in papers, these things are used a bit freely. So most of the time people talk about validation when they mean verification. And often people do verification, but they don't do validation, because validation is very hard. Validation means you need an experiment. And that's why I'm so, let's say, admiring of what you guys do in Limerick, because you have real problems in front of you. You're not just dreaming them up. You have real experiments. You have noise. You have modeling. You have measurement errors. You have things that don't run. You try to make the same experiments 5 times, and they are every time different because it's very difficult. And if you talk about biomechanics, it's even more difficult because you cannot open the brain of someone every day to try to see if it changed. So you have to do with extremely little ammunition in terms of data. So keep that in mind. Are we solving the right problem? It's called validation. And are we solving that problem correctly? Are we solving the problem right? This is called verification. And this is what we do today. We talk about discretization error, and numerical error. That's it. Only. So very simple. Problem is that if you want to know if your solution is correct, which means we assume the model is correct. We will not talk about models. We will just assume we have one model and this model works, and we want to solve the problem. That's it. Now, what is how do we do that? Because we don't know the exact solution to any of our problems, because otherwise we wouldn't be solving it numerically, would we? So if we don't know the exact solution, how do we go about trying to figure out what is the error? Because we don't know what we're comparing to. And that's something that I will briefly talk about, but not too much. So I will focus on discretization and how it's linked. To ours. Okay. Now, what is the usual way in which you solve engineering problems? So you start with this component. This is a propeller. It doesn't matter what it is, really. It's made of some material. So you have some models. You have the geometry at the top left. You have models at the bottom left. And in models, again, we have all these things: elasticity, plasticity, crack growth, interface laws. You have, force displacement curves for cohesive law models, damage model, non-local damage model, coupled, non-linear, non-local plus gradient elasticity and gradient damage models coupled together, like for concrete, for example. You have multi-scale, because sometimes one scale is not enough. You need two. Then you need to look at pull-out of fibers, fiber breakage, interface fracture, grains, dislocations, molecular dynamics, quantum, whatever. So these things it's like infinite here. I mean, it's you can take models and put them together, and you will end up with an arbitrarily complex set of models. You need to make a selection. Then once you've done that, we said that we had done that. Let's say we select elasticity because we wouldn't like this propeller to plastify. Would not be so nice for the ship, I guess. So then you need to discretize that geometry. And this is the point called discretization, which means generating a mesh. So you want to generate a mesh of that thing. So here the geometry is more complex, but not horrible. And you probably can generate a mesh which looks nice. And then now the next question is, once you have this mesh, what do you do to get the numerical solution? And if you have the solution, how do you know that the solution is, how correct the solution is, and where? It could be very correct in the blue region, but completely wrong in the red region, very likely, by the way. So how do you do that? That is the cycle that you are working on. And same thing for biomechanics, but in biomechanics, you start from an image and you don't start from a CAD model, by the way. Here, this thing is a CAD model. So usually some designer was sitting around, not sitting around in the negative sense at all, but was sitting for a long time trying to make a nice looking geometry. or a functional geometry. And they have a lot of know-how in their brain. These people are really outstanding and amazing because they know what they feel, what should be this angle here, this fillet radius, such that the concentration in stress will be allowable. But sometimes they make mistakes because they don't know that the boundary conditions will have slightly changed, and they are not engineers most of the time, they are designers, drafters, let's say. So for brains, obviously, we don't have the blueprints of the brain, otherwise that would be known. And that means that we have an image, and that image needs to be discretized. This is the same case for Sophia in the group working on astrocytes. She doesn't have a blueprint of the astrocyte. She has an image of it, and she needs to discretize that thing, get a solution, and compare and look at the quality control, which means compute the error of the discretization for that particular problem. And here, of course, in biomechanics, the added problem is that you don't know in advance what the model actually is at all. So you could argue that for engineering, here you can do experiments in the lab, and you can break stuff repeatedly to know the fracture energy, for example. But here, you can't do that for a person. I mean, you're not going to make experiments on people. This is absolutely morally and ethically unacceptable. So you need to just build on knowledge that you have acquired over not so long, because imaging is not so old, really, and quality data is not so easy to find. And this is also a topic of Driven, which is how do we build a digital twin? Because a lot of the information that we have here about that engine could be acquired in real time during the life of the engine. So this propeller is on a ship. On the ship, you can put some sensors. You have maybe temperature sensing. You have strain sensors. You can put also a lot of optical sensing devices and so on. But then, okay, you would like to know in real time what's going to happen to the system, because although you did these experiments in the lab, you know that in real life, when you have this ship here, you see this little guy here next to the propeller, to give you an idea of scale. When that thing goes in the ocean, you have all sorts of things happening. You have corrosion, you have algae getting stuck on that thing, and you can hurt, you can hit, these plastic islands, or I don't know what can happen. But anyway, at the end of the day, what you have in real life is not what you have in the lab, that's for sure. So that's why people come up with digital twins, because then the idea is that you put sensors on the thing, and as the sensors are coming up with the knowledge of what happens in the field, the data is being fed into the computer, which is this digital twin. And because there are smart people trying to come up with models from data directly, then you can say, okay, I need to change my model because this propeller is actually failing now. There is a crack, so I need to model that. Hopefully you don't get to that level, but you get the point. So depending on the data, you might want to change the model you use and then do another simulation to try to figure out what will happen to the system if they keep going in the sea with that propeller and they don't come back to port, for example. How long can they go before it definitely fails and you need to repair in the middle of the ocean, which is definitely not wanted. All right, and well, now we are in the COVID era, so probably everybody has thought about this, passport that tells you whether you're vaccinated and whether you have antigens and whether whether you're allergic to penicillin or whatever. All these things could be on a chip. That chip could even be, under your skin. Why not? And that thing could be also taking measurements as you go. If you have one of these watches here, they take my oxygen level in the blood. They take my heart rate, which is currently 70. So I'm very excited by the course, apparently. And these things will develop clearly, and they will allow us to make decisions on medical treatments for people. And so I believe this is what our partners in biomechanics and in the Driven project are working on. So yeah, so in the long run, this is what in the direction in which I think the field is going. So this is a very complicated slide. If you take a look at, but I think covers pretty much what the audience is working on. You see, so if you take, let's say, one of these fancy A350s, very silent aircrafts, which are made up of composite materials, you see that the materials are, as you know, made up of multiple layers. And these layers are very complex, as we said, and you have fibers running through them and so on. So you're going to need upscaling techniques in order to come up with proper models. But these techniques, we believe, could come from data and experiments. So that graph here comes from a collaborator in Bristol, Stephen Hallett, because we were working at the time with the Bristol composite team. And they were looking at fractures in sort of, composite panels composed of that would be used for bolted joints. So like, for example, that one here has a hole, and then because of that hole, you have concentrators. The hole acts like a stress concentrator, and you have these cracks that run in different directions that you can actually measure. And again, what you'd like to do is you'd like to look at this thing, and this is a very old slide because we had this idea a decade ago at least. Now, finally, it's starting to take shape. So again, in academia, things can take really long before you, from the first idea to the final one. So then you measure things, and you try to use machine learning, and you try to come up with the model that is the best one. This is a figure made by Frank Langbein, a physicist in Cardiff, with whom we were working, and with Sophie, who was working there as well in Wales. And then at the end of the day, we have a priori knowledge about the model. We measure stuff, right-hand side. We select the best model based on a priori knowledge and measurements. We fuse data and measurements, and then we come up with a model which can be evolving in time. So this is like the, what people would call the holy grail, in my opinion. And this is, of course, why we need reliable methods to solve, because in here, hidden is the ability to solve a problem accurately using a complicated geometry. And this is what we're talking about today. So these digital twins. So why do we need to even talk about the accuracy of these models? So during the course, I'm going to talk about discontinuities also, because this is something that comes up all the time, especially when you look at problems like composites, because in composites, you are almost nothing is continuous. Everything is discontinuous. I mean, those of you working in this will probably agree with me that you have to contend with situations which are very heavily discontinuous. So, for example, if you take, let's say that you take an Airbus, just to say something, or an Aston Martin car. You look at these things, from far away, they are mostly continuous. So the continuous assumption is completely valid. Everything's fine. As you zoom in this, if that allows me to do it, as you zoom in, you see a lot of discontinuities. And the more you zoom in, the more discontinuous things become, right? So for example, if you take, let's say, the Airbus, so you zoom in, you see this bolted joint. You zoom in, you see these 100 plies. This is from Pierre Keffredin's PhD thesis in L'Implication. Each ply is 0.125 millimeters, so 125 microns. And you have these little fibers running in this direction, that direction, this direction, that direction, in order to make a fancy composite that actually works for what you're trying to do. So resists bending and torsion and compression and tension and shear and so on. So here for the Aston Martin thing, you have a printed circuit board. That thing is made of certain, like solder joints. These solder joints are made of grains, and these grains are subject to fracture. And when you load the car in terms of thermal loading, so you start the car in the morning, get out of your garage, go to work, stop the car, so you have a heating cycle. It heats up, stands constant for a while at 90 degrees more or less, and comes back down. and then cools down again. So these cycles will lead to thermomechanical fracture. That we did with Bosch, and that was done with the ADS. So same thing for the brain. I'm not going to go through that in detail, but if you zoom down into the brain, you get to the scale where Sofia Farina is working in the astrocytes. But if you look at it from far away, it just looks like a sponge, which is a bit squishy, you know, as the neurosurgeons describe it. So depending on the medication that people take, it's more or less squishy, but it's basically has a certain consistency, and you don't need to know that it's made of astrocytes and neurons and so on. At least you don't need to explicitly take them into account. But if you wanted to know what went on exactly at that neuron and try to figure out whether that neuron will be damaged during an impact, for example, then you'd need to know where that neuron is relative to the global scale. And so that's why the multi-scale methods are actually useful in practice. And because we are going down in scale, we also need to go up in terms of discontinuities. So the more you go down the scales, the more you go up in terms of discontinuities. At some point, you end up at the atomic level again. And then, you know, you have wave functions and things become, again, quite continuous because you can write everything in terms of Schrödinger's equation. As far as we are interested, we are always in between here. We are in the middle range. We are never too much at the large scale dealing with continuous things, and we're not too much down in the, you know, in terms of discontinuities, but we are somewhere in between. Okay, so now I'm going to give you an idea of so just give me a second because I need to switch presentation. If there is any question before that, it would be really nice to have them now. But if not, I can easily continue. So that is, now I am done with the introduction. I'm going to talk to you about what people today can do about meshing. And why? Simply because if you listen to, because each problem has multiple view angles. So if I teach you IGA, I will teach it in a certain way because I have my own experience of it. And other people will teach it in a different way because they have their own experience of it. And of course, there are certain things that are true completely. So there's no discussion. They are independent of the viewer. But there are other things that may be said in different ways depending on who the viewer is. And that's why I would like to start by telling you a bit about meshing, because meshing is something that a lot of people speak about, but not so many people do. And a friend of mine does that meshing every day for many years, and in fact, many decades now. And his name is Jean-François Remacle. And he is not only a friend of mine, but he's also a guy who created the software with Gauzen. He created the software called Gmesh, which perhaps you guys know and use maybe even every day. And that piece of software he created quite a long time ago. And after that, he decided to move from the original idea of Gmesh, which was mainly tetrahedral elements and triangular elements, to try to see how he could generate hexahedral elements. And I'm going to tell you about that and why this is important. And this is going to be a long motivation for IGA, but I like to motivate what I talk about because otherwise you will assume that IGA is a necessary step in a certain direction. But I would like you to be able to make your own mind as to what is useful about IGA, what works well, what could be improved, so that you can decide what research you want to do in that field, because after all, that's why you're here. So I wouldn't like to bias your view. I would like to tell you as unbiasedly as possible what I know, and then so that you can make up your mind and you can decide what you want to do with it. This paper is really amazing. So the title of the paper is "One Machine, 1 Minute, 3 Billion Tetrahedra." And Professor Stéphane Bordas is leading his ERC advanced grant at the moment in Université de Louvain-la-Neuve. Université, yes, Catholique de Louvain, so UCL in Louvain, here, Université Catholique de Louvain. And yeah, he's been working on meshing for forever and ever. And he, as I was saying, he moved from tetrahedral to hexahedral. I'm going to tell you afterwards why that can be useful, and maybe you have an idea already. But as you can see, he was able to generate, let's say, 3 billion tetrahedra in 1 minute on one machine. So this is outstanding, right? So I'm telling you that because this is the state of the art, more or less. So when someone tells you meshing is difficult, then you can tell them, yes, sure, it's difficult, but take a look at that paper. At least some people know how to do it. And of course, there are limitations to everything that is said, okay? So we're not talking about arbitrary geometry, but this is something you need to know, that if you want to generate multi-threaded Delaunay tetrahedralization of volumes, this is possible, and you can do it with Gmesh. And now the team of Jean-François Remac is working on extending this to tetrahedral elements. So if you look at this thing here, this is a tire. So, okay, it's a complex geometry. It's not the most complex you can think of because you don't have the reinforcements put in here. But still, if you look at these little dents and the tread of the tire, it's not so simple. And if you then look at what is important in this slide is the last one. So in that case, it took 190 seconds to generate a mesh, which was made of, well, you see, 123 million tetrahedral elements. So first thing was to generate the mesh and then to refine the mesh because it needed to be refined in certain areas, right? And the total time after refinement was about 3 minutes. So this is super fast. So that means that even with super complex geometries, you can still do it. So generating the mesh is one thing, but keep in mind that some people are working hard on this and making it work. They have another example which is of interest to composite people because it's a problem of, let's say, a rather dilute solution of little rods inside a domain. And the idea is that you need the mesh to be conformed to the rods. So can you imagine? So you have these little needles, these little pins that you randomly distribute into this box. And you need to generate a mesh which is conforming to these rods and is properly dealing with the discretization of each and every of those rods. This is tough. And this is done using tetrahedral elements. So you see here 324 million tetrahedral elements. So it's not 2.5, right? And here 721 million tetrahedral elements in what? 135 seconds. So not even 3 minutes, 2 minutes and something, 2 minutes, 15 seconds. So, I mean, that I call impressive. And that is really some of the best stuff you can do these days. So it is possible to mesh things. And it is done very well in certain cases. Now, why is everybody talking about things like mesh-free? Why are everybody worried about these elements? Why are people constantly trying to find methods which are not relying on a mesh? I think that is the question. That's why we are here having this discussion, is that, apparently it's not so nice. The situation is not so good, although we can generate these huge meshes. It's not so appealing because we are still in cases where people are making huge discussions, producing papers on why it is that we need to avoid generating the mesh. So therefore, it is necessary, as far as I'm concerned, to understand why it is that these people are having these discussions. So of course, it's going to be problem dependent, but I have to at least give a few things which are certain, because you need to get out with a proper understanding. So if you are someone who works in proper finite element analysis and you use ANSYS, Abacus, Nastran, whatever, PAM-Crash, maybe not PAM-Crash, Nastran and so on. Okay, you're going to have to look at problems where you need to discretize the volume. You're going to use these little tetrahedral things. And with this tetrahedra, you're going to cover the whole volume. That's the point, right? Now, the question is, what are you going to do with these elements? And why is it not just nice and sufficient to use that very nice piece of software that can generate arbitrary numbers of tetrahedral elements, more or less, in a reasonable time? So first of all, because you cannot always generate the mesh, there are cases where it will fail. That's the first thing. That's what we said. It's not provable that you can always generate a mesh. Second is that these little buggers here are not so cool as elements, let's put it this way, to speak like my teenage sons. They are not so nice because, and I would like to go back if that will allow me, because they have several problems. The first is that they tend to be very stiff. That comes from the fact that inside this tetrahedral element, the strain, which is the gradient, so the derivative, is constant. It means that the approximation is linear inside the tetrahedral element. And because of that, you need really many elements in order to simulate things like bending of a beam. So if you were to look at a beam bending problem and you used only tetrahedral elements, you would see that the beam would barely bend. And the problem would be even worse if you were to tackle a problem of bending under severe constraints. So for example, the bending of a beam, which is constrained at the top, at the right and left, and you try to bend it. Or even worse, if you take a piece of soil, like which is constrained on the three edges of a rectangle, and you try to press on it from the top. Or if you solve the problem of the driven cavity model in fluid mechanics. So the driven cavity model using these elements, you get 0. So the solution is almost machine precision 0. So it means that there is no deformation. So you try to apply deformation onto an element, but this leads to 0 deformation. And this is only based on geometry, in fact. So you can show it in certain cases. You can prove it by hand in a few lines. I'll show you later if you're interested, that you will have no deformations. The thing will simply not deform. And that's a problem. And this is called locking. And this is called locking. So locking is the inability of an element to deform. And that happens for cases where not only when you have Poisson's ratio close to 0.5, which means that the material is incompressible, that's one case, but it happens generally when you have very small parameters in your partial differential equation. So when you have shells which are super thin, for example, or then you will have the problem of locking as well. And the reason is simply that you will get very huge terms on the diagonal of your matrix. And therefore, when you invert the matrix, the displacement that you get will be very small, because on the diagonal, the spectrum of the matrix will be such that you have very small values and large values. And these large values will lead unavoidably to very small solutions, right? Because if you do KU equals F, but K is huge, then U is small if F is constant, right? Because if you have K equals 1 billion, 1 billion times U equals 1, then U equals 1 over 1 billion, which is 10⁻⁹, and that thing is so small that you can't see it. So that's why locking takes place. It's not only due to Poisson's ratio, that's one case. It's also due to very small values in the partial differential equations. And that can be insidious, and sometimes you don't see it. So that's why you need to be careful with that. And these elements are notoriously bad for this. So that is why people came up with alternatives, but not only IGA. People came up with a lot of alternatives. I was talking about mesh-free methods in the introduction, so I won't do it again. If you're interested, I spent a lot of time thinking about that, and I would be very interested in having a discussion. And in our group, Patrick Souchde, who is at the Fraunhofer, was at the Fraunhofer, and is now Marie Curie here, is working heavily in mesh-free methods. So he has a very, very deep knowledge, and not only industrially, because he works at the Fraunhofer on industrial projects, but also mathematically, which makes Patrick a wonderful person to work with. So if you look at alternatives, okay, that again, there are literally, and I'm not kidding, hundreds of papers on these things. I mean, it's maybe even thousands. So how do you deal with that problem of locking? So there are many ways, and you all know them. B-bar methods, there are the Huwa-Shizu formulations, hybrid methods. You can use stabilization methods, or you can use higher order elements, for example, quadratic tetrahedral elements, cubic tetrahedral elements. You can increase the polynomial order. And that's the first thing you would do. So in industry, if the thing locks, people are used to it, they will say, okay, I'm just going to use a P2 element, like as mathematicians would say. So it means I will use a quadratic element instead of having linear displacements, constant strain, I will use linear strain, quadratic displacements. Then the locking will somehow disappear. But then I have to deal with elements that have, if it is a triangle, 6 nodes, if it's a tetrahedral, even worse. So these 6 nodes lead to distortion of the element. So when you generate the mesh, you need to be wary that the mesh is not too distorted, because if the mesh is too distorted, when you do the mapping, and that would take a full finite element course, which we can do another time, from the parent element to the physical coordinate system, this mapping becomes ill-posed, so it becomes non-invertible. And if the mapping is not invertible, then obviously you can't do the change of variable, and therefore you cannot write the weak form in the parent element, and then you basically have an element which is as good as useless. So you have to be careful not to distort the elements. So that's why P2, meaning quadratic elements for tetrahedral elements, are used. But one, they are super expensive. When you talk to industry people, they tell you, oh my goodness, I'm not going to use quadratics, it's too expensive. Therefore, most of the time they use linear, although it's not necessarily accurate. And then on top of that, they are distorted more easily. I did that during my PhD, and I could figure out that to generate a mesh of quadratic elements was significantly more complicated than generating a mesh of linear elements. And so you need to be aware of that. So the second thing is, okay, I don't like these triangles because apparently they don't work. So I'm going to replace them by other things, like these little funny shaped marbles, right? These polyhedral elements. And these polyhedral elements are cool because why? Well, simply because they have a lot of flexibility. They don't need to be triangles. They don't need to be tetrahedrals. They don't need to be cubes. They can be polyhedral elements, so little grains of some sort. And if you can generate a Voronoi let's say diagram for the volume, which is nothing else but these things, which is the dual of the Delaunay triangulation, then you can deal with it. And we did that with INRIA, our partner in Driven, and this is called, this is a team of Bruno Lévy, who is now the head of the INRIA Center in the east of France, in Nancy. And what you can see is that you can use these tetrahedral elements. That was in collaboration with IIT Madras, Sundararajan Natarajan. And we were able to solve these things with Amrita Francis, our PhD student. So these things are doable, definitely. You can use polyhedral elements. You need a mesh generator for them. And this is the work of Bruno Lévy and his team. So that works. Okay, all right. Then you can use what's called virtual elements, which are generalization of finite elements. So these virtual elements, they came about by Franco Brizzi, and So as you know, Franco Brezzi is the last B in the LBB condition. So in the, I cannot pronounce the L, so I won't do it, but Babushka-Brezzi condition, which gives you stability conditions for finite elements. Professor Brezzi is the second B, and the first B is Babushka, no one other than him. So this is a very important condition that tells you how to select approximation spaces for problems with constraints. And virtual elements came about and were generated by him and his team. And the idea is that you would like to use elements that have arbitrary shapes and that can be linked together using arbitrary interfaces. So what he did is he took some statues, discretized, let's say, made an outline out of it, and used any arbitrary shape of a statue as a finite element. So it's basically you can use arbitrary things and it will still work. In that case, they are called virtual elements because the shape functions are not known a priori. These functions are calculated whilst you solve the problem. This is quite a nice topic. Recently, HHO came about, so if you're interested in this, I can link you up to Franz Schuli in France, because he's worked with EDF, Électricité de France, about that method a lot recently, and he has an extremely strong background in this. It's essentially a high-order method, which is a bit similar, I would say, to discontinuous Galerkin on arbitrary shapes, which gives you stability. So this is a very, very cool thing too. Then you have people who have worked on scaled boundary finite elements. For example, Chongming Song, who came up with the idea with Wolf in Switzerland when he was doing a postdoc, but then moved it back to Australia, where he has a whole group working only on that, or mostly on that. And Sundararajan Natarajan worked on that with him. If you like to know more about this, let me know. This is essentially a way to reduce it's very useful for problems with singularities. It's extremely precise for fracture problems, for example. And it decreases the order of the problem by one. So if you have a 3D problem, you solve a 2D problem. If you have a 2D problem, you solve a 1D problem. So it's a bit like boundary elements. And finally, smoothed finite elements, for which we wrote several review papers. I can tell you more about that if you're interested. It is a way to use exactly the same elements that are actually locking, so these tetrahedral elements, but without locking. So you actually can overcome the locking by doing something very similar to Huwa-Shizu formulations that allow you to, instead of integrating over the area of the element or the volume, you integrate over the boundary. So this is the background, and I will give you references on that. So again, one thing, you can use polyhedral elements. That's what we did with Bruno Levy and Claudio Lobos in Chile. You can use virtual elements. You can, for example, see this paper, Hitchhiker's Guide to the Virtual Element method, which is really very clear. So you can read this. Smooth finite elements, those are the references. I'll give you the slides, so no need to frantically write things down. It shows basically theoretical studies on smoothing and on the approximation in smooth finite elements, and scaled boundary and HHO. So these are the references I was talking about just before. Okay, so the idea is, as we said, that we would like to get rid of the mesh. So that's the thing. Okay, so the motivation is this. As we said before, you have a complicated geometry coming from images or from a CAD file, doesn't matter. You want to discretize that guy, and you want to do it in a way which is not going to give you too much of a headache and gives you results which make sense. They don't lock, they are not too stiff, and they are sensible. So to do that, there are really two ways. And now we're getting closer to IGA, finally. You guys will probably be happy about that, because you probably think that I'm spending far too much time explaining why we need or we don't need this method. So handling interfaces numerically is the question. Interfaces could be the boundary of the object, as we said before, but it could be also a moving interface, like in the case of Sophia with the astrocyte moving around, or it could be biofilms. You know, if you model biofilms, it could be a tumor, it could be the front of a COVID pandemic, it could be many things, right? So these things that are moving in time are very, very important. So fractures, you know, a solidification front in the Stéphane problem, it can be anything where there is some sort of weird looking interface. You know? Or it could be actually materials with several phases, you know, like these. Yeah, okay, you get the point. So now there are two ways. There is one way is you couple, the other way you decouple. And IGA is the left, and things such as implicit interfaces, immersed boundary methods, extended finite element methods, cut finite element methods, cut FEM, and so on. These are the right-hand side. And the idea is that, okay, well, you have basically half the world believing in one and half the world believing in the other. Well, not really, but you basically have two ways to approach the problem. And depending on your problem, then one will be more or less well-suited. And that's what you need to decide when you go about solving such a thing. So how do we do that really? All right. So the first thing is you need to decide what really is the data that you have. So let's see. What I mean by implicit, I won't go into details unless you want me to, but implicit boundaries, what I mean is that the boundary is not explicitly followed by the mesh. So this mesh here is made of what is called quad tree or oct tree. These are elements that are all squares, but they do not stick to the bumper of the geometry. You know, so the geometry is whatever it is, it's independent of the background mesh. So this is why I call this decoupling the geometry from the analysis, because the analysis, meaning the mesh, is not conforming to the geometry. But you could say that this geometry that you see here, this little star-shaped thingy, that thing could be the domain itself on which you want to solve the problem. That could be the case. It could be the propeller. You know, you could decide to take the propeller and immerse it into this finite element mesh. And this immersion of the propeller in the finite element mesh is called immersed boundary or implicit interfaces or cut finite elements or extended finite elements or generalized finite differences, partition of unity finite elements. There are so many names. This is why the whole literature is a bit confusing. And that's also why I split it into 2 and not into 100. Because if you look at the different methods, you could think that on the left you have 50 methods, on the right 50 methods, more or less. But if you categorize, you have basically 2 families. One keeps the geometry and then the analysis together, and the other takes them apart. And we have worked with both. So probably that's why I like putting in that light. So here, that goes into a little bit more detail about what I was telling you about the work of Thibaut Jacquemin about collocation. So the idea is, if you do collocation, you would like to do mesh-free. So what is mesh-free? It is a set of nodes. Here you have a grid in the background, but this is not necessary. And these nodes are the nodes that are describing the geometry of this rabbit. And you would like to be able to describe the geometry of that rabbit without too much hassle. That's the point. And even though it's not Easter, you can definitely do it easily. So I won't go into detail about the collocation scheme. Now, what is IGA? So the idea is that you want to simplify the connection between CAD and analysis. Why is that even a question? Because the first problem is that some person sits in an office, designs a propeller. Some other person creates a mesh for this. if you read the 2005 paper by Tom Hughes, and if you read his book as well, which is here, Isogeometric Analysis by Cottrell, Hughes, and Basilev. Well, if you read this at the beginning, there is a part that talks very clearly about how much time it takes to generate meshes for, let's say, industrial problems. And I think it is saying that it takes 80% of the total analysis time. Yes. Mesh generation accounts for, so I'd like to quote this because it's very nice. So the 80-20 modeling analysis ratio seems to have a very common industrial experience, and there is strong desire to reverse it. But so far, little progress has been made, despite enormous efforts to do so. The integration of CAD and FEA has proven a formidable problem. It seems that fundamental changes must take place to fully integrate engineering design and analysis process. So it's saying that it takes approximately 80% of the time to model the problem. So, you spend 80%, and this is page 2 of the book. And so you take 80% to generate a mesh for this thing and 20% to analyze, which truly, is not exactly what you'd like, because you'd like to spend more time in analysis and less time in preparing the thing, right? I mean, that sort of makes sense. Okay, so what can you do? Well, every time let's say that you have here a stress concentration, which is something too large and you don't like it, right? Well, then someone needs to go back to the drawing board and draw another propeller, and then they will generate a mesh for that propeller again, right? Of course, you can parameterize the volume and you can parameterize the mesh, but if your changes to the geometry are too extreme, then when you move to the mesh generation, then you're going to have to regenerate it by hand. So the idea of IGA is to go beyond that and say, I don't want to regenerate the mesh every time I change the geometry. I would like, it's like a dream. That's what I like about this method, is that it's a bit like Elon Musk, wanting to go to space and pushing his dream to the end. Here, the dream is, I want to make the geometry, the mesh, insensitive to the geometry. I would like to be able, what would be the optimal thing? That I think that is the first question that the inceptors of the method must have asked themselves. What is the optimal situation? So the optimal situation would be, I don't want a mesh. But then if you go back to 2005 and you look 10 years back, you see all these mesh-free methods which were not really mesh-free. So maybe you tell yourself, well, maybe that's not exactly what I want, right? Because however smart I can be, I always, sorry about that, will need a mesh. So I will always need a mesh. And I'll take a break in a few minutes so that you can breathe a bit. We will always need a mesh, whatever happens, in some way. I mean, of course, this is not completely true, because I hope that are you still seeing the thing or not? Yes, okay, because I made some changes, so sorry about that. Just okay, good. Yes. You still see it? Yeah, okay, good. So I would like to make a mesh, but I don't want to actually touch the mesh once I change the geometry. So I would like to modify this thing on the left here, such that every time I modify it, the solution is directly computed. I don't want to have to modify the mesh again ever. Right? That's the idea. So, and that was, I think, what prompted the isogeometric idea, really. And at least that's my view. So how do we do that? We would like to have, in fact, so what would be the optimal thing, really? So we start from a CAD model. We would like to solve directly from the CAD model. We don't want this mesh here, and we don't want mesh free. Okay, so we don't want to put collocation points like on the rabbit for Easter. No, we don't want that. We just want this beautiful geometry to be the stuff we compute on. That's what we want. How can we do it? So that's what I think they asked themselves when they wrote this very nice paper in 2005. So, well, so how, maybe the next question is, how is the geometry of this thing described? Because maybe if we know how the geometry is described, we can know how we can work with it to solve a problem. And it happens, and that's what we'll talk about afterwards, that the geometry of this thing is described using certain functions, which the designer doesn't need to know about, but they are called B-Splines, Bernstein polynomials, and non-uniform rational B-splines. So I was saying no jargon, so here I cannot avoid it because that's the name of these things. And they are rational polynomials, and they allow you to shape anything. So if you play with CAD a bit, you know that if you take, one cylinder, another cylinder, and you do a subtraction, so you can look at the intersection between one cylinder and the other cylinder, and you'll get something out of it, right? So that is called primitives. So you take primitives, you put them together, and you look at the intersection between these things, and it gives you another geometry. Right. So the nice thing about these non-uniform rational B-splines, Nurbs, is that with them you can generate any arbitrary conic sections. So conic sections, if you are not too much into geometry, are basically all the shapes that you can get by splitting a cone with a plane. So if you take a plane, you split it, depending on what the angle is that the plane cuts the cone, you can get either a circle or an ellipse or parabola or a hyperbola. So that these things are called conic sections. And these conic sections, they can be reproduced exactly using Nurbs. It means that if you have a circle here, you can reproduce it exactly. If you have a parabola here, maybe I don't know where, anywhere, you can reproduce them exactly, and so on. So it's super nice because the designers really like it. What they can do is they can look at whatever shape they want to make, and they simply generate these Nurbs, and they get the shape. And then what we normally do, let's say we have a circle here on the left. Well, if we have a circle in finite elements, I was telling you since the beginning, we discretize the circle. So what does that mean, discretize the circle? It means we have a circle, it has an infinite number of points. Well, you make it a polygon, right? That's what you do in finite elements. You just say, okay, I want to have a pentagon or a hexagon that will represent the circle, that's it. And then I will solve on that pentagon or hexagon, and I will assume it's a circle. Obviously, it's not. So you have all these corners and weird-looking things. It's very painful. If you do electromagnetics scattering on that sort of shape, which is not a circle but now a pentagon, you will get spurious oscillations due to the corners, because the corners, Helmholtz equations doesn't like corners. So if you try to solve the problem on that thing, you're going to get spurious solutions. If you solve fluid mechanics problems at high Reynolds number on a bluff body which doesn't have a shape of a disk but has a shape of some weird-looking hexagon, then you're going to get turbulence, and you're going to have to get rid of that because they are not physical. Because the real problem is a disk; it's not a hexagon. So in other words, sometimes having a simplification of the geometry actually leads to completely wrong physics. And that's not what you really don't want that at all. So you'd like to keep the geometry exactly as it is. And on top of that, if you can do that, then you don't need to go back to the geometry in the first place and mesh it again every time you change it. Let's say you don't like this circle, after all, you'd like an ellipse. Then if you need to mesh the ellipse, this hexagon that you had doesn't work anymore because you need to elongate it and make it look like some elongated hexagon, right? Which is not regular anymore, let's say. And then you need to go back to square one again. And so what is the optimal thing from the perspective of IGA? The optimal is you generate a geometry, and then you do not need to generate this mesh. But then how? Because this mesh is very convenient. It serves a lot of purposes. The first purpose is that it sticks to the geometry. As we said, it doesn't stick very well because a circle becomes a hexagon, not nice. Second thing it does, it helps you integrate the problem, the weak form. So here I have to use some words which I hope everybody sort of heard of before. But if you didn't, let me know. I'll give you some short notes on that. You need to integrate the weak form, and the elements are very useful to do that. That's the second thing. And what is the third thing that the mesh does, actually? So integration, geometry, and maybe the most important is for the shape functions, is to devise the shape functions. Because with the mesh, you can say I have these little hats, and each point in the domain is a node. It has a value of a shape function that looks like a pyramid or a hat. And this hat function is going to be the approximation function. And this is the problem. So this is what IGA does. It allows you to do all these three things within one. So it does the integration, it does the discretization with the shape functions, and the geometry in one. I think that's the beauty about it. And basically, the idea is, okay, these shapes here, they are governed by a certain B-splines, Nurbs, or whatever it is. And then I'm going to, normally I say, okay, I don't like these B-splines, they're too complicated. I make some hexagon out of the circle. And then I lose the circle. I actually forget completely that I had ever had a circle. I don't know anymore that it was a circle. Now it's a hexagon. But this hexagon is quite nice because I can generate shape functions that are 1 at the top of each node and 0 everywhere else. And I can go from node to node, and I have these finite element shape functions that are super nice. How do I do it with Nurbs? So what you do is exactly the same. What you say is, okay, I have these Nurbs, they create the geometry, but now they are also going to be used for the shape functions. So the shape functions, which are usually Lagrange polynomials, which are 1 at one point, 0 at all the others. Now, they will not be like that. They will be Nurbs. They will be non-unified, uniform, rational B-splines. In the simpler case, they will be B-splines, which are polynomials. Non-uniform rational B-splines are rational polynomials, and they can generate arbitrary shapes. So that is the whole idea of IGA. You get rid of the mesh, and you go directly to the solution. And this is in the 2005 paper, which is the paper on isogeometric analysis, cited thousands of times, I think now, and which has had an enormous impact on the solution of problems. So then later on, there was a second paper which we co-authored with Tom Hughes in 2013, and it's called Isogeometric Boundary Element Analysis Using Unstructured T-Splines, which goes one step beyond isogeometric analysis in the sense of finite elements, because it allows you to get rid of the mesh entirely. So at no point in the analysis is there any mesh. And after that, we worked on the use of this method for optimization of shapes directly from the CAD, and that allowed us to be completely out of the mesh generation process. What you therefore do is you take the shape and you describe it by Nurbs. This is what the designer tells you. Then you transform that into something that you can solve with, and you solve directly from the Nurbs functions. And you perform, let's say, a stress analysis, but for all intents and purposes, you can do that with anything. Okay, the next question before we take a break, I'd like to at least finish that introduction properly, because then we'll talk about something else. What we said is, okay, you take the CAD and you solve directly with the CAD, but for that you need to know how the CAD is actually described, right? So the first thing is that the most by far used technology in practice is called Nurbs. Non-uniform rational B-splines, we'll talk about it. This is the industrial standard. Everybody uses this in industry. It has one drawback, which is it is not watertight. So if you're new to the field, you must be wondering what we mean by that. So there is a very nice example here from the Rhino 3D website, which shows you how to couple two different Nurbs together. So one is the spout of this tea container, the teapot, and the other is the body of the teapot. And if you zoom here at the interface, you see a gap. And you see a gap because there is no necessary continuity between the shape functions associated with one and associated with the other. But we'll come back to that later, because for now it must be confusing. And the second problem is that you do not have local refinement in Nurbs. It is not easy to locally refine the mesh. I mean, let's say not the mesh, but it's difficult to speak without talking about meshes. It's not that it's not a mesh, but you cannot locally refine the representation easily. You can, but it's not trivial. We'll see that later as well. So what you can use instead is a technology which was incepted by Tom Sederberg in Utah, for which he has a patent and created a company as well. Company is called T-Splines, and the technology is called T-Splines. And these splines are watertight. That's what we use on this propeller here. And you can do local refinement, like with T-junctions that you can do in octree and quadtree usually. You don't have trimming operations, and you do not have linear independence, which means that the shape functions that you come up with may be linearly dependent, which could be a problem if you want to solve, let's say, real problems, because you end up with rows and columns which are linearly dependent, so you don't want that. And finally, the Pixar Studio and so on came up with other types of surfaces, which are called subdivision surfaces. So there are quite a lot of them. And those are watertight, flexible, 3D printing. Oh, someone still sees only slide 14. Is that the case for everyone?
I am in 18.
You are in 18, okay. All right. Okay, good. Thanks. Okay, sorry. So yeah, so all these things are boundary representations. And so the question behind that slide, what I find interesting is that, you know, there is no such thing as a free lunch. So we just said, now we want to use the CAD for analysis. And normally we generate that, you know, pentagon or hexagon on the circle, right? So we forget the circle. Now we say, no, I don't want to forget the circle. I really like it. I want to keep it. So, well, okay, fine. But what tells you that the shape functions that describe the circle, so these things that make it a circle, what tells you that those will be well adapted to solving the finite element problem? You know, what tells you that the PDE, the partial differential equation you solve, will be well solved by these equations, these shape functions? You know, what tells you that? Nothing. And in fact, it's not necessarily the case, but sometimes for some problems, it is really, really super helpful. So that's the question. Now, that is why people came up with new terminologies, like in the COVID era, we came up with new words, you know, like confinement and social distancing and all these things. You know, our vocabulary got significantly enriched during this period, although our social life was significantly impoverished. But here we came up with new terms. So the terms were, for example, analysis suitable B-splines, or analysis suitable shape functions, geometry, analysis suitable geometrical descriptors, and so on. So these things did not exist before IGA, because before IGA, people didn't work on using the shape functions generating the geometry in order to solve the problem. Okay, so I think it's a good time to stop for a break if you would like to take one. And this way I can reassemble a few things. And yeah, so maybe take a break. I don't know, Katerina, how long you'd like that to be. I can sort of adapt.
I propose a 15-minute break, so we reconvene at 11:20. Is that okay with everyone and you, Stéphane?
Yeah, for me it's good. It will give me a bit of time to organize the things, because I had to plug in my computer. Some stuff started going a bit haywire. Okay.
So take a break, stretch, coffee, and come back in 15 minutes. Thank you, Stéphane.
Yeah. Okay. Thank you so much, Katerina. See you soon.
See you.
Hello, can you hear something? Yeah, is it better or worse than before? Because I sort of changed some. It's worse?
Same. No, same.
Okay, good. Okay, so I'll do a bit of discussion on B-Splines. At some point, I'll try to share my iPad connection as well. So it's going to be maybe a bit hectic. Maybe it will fail. And so you'll have to bear with me a bit, because I'd like to do some writing a bit so that it's not like a movie theater. And that. So it's working well? Okay. Katerina, everything is okay?
Yes, all good. You can go ahead.
Sorry, I had started the streaming at the same time, so obviously that was a bad idea. Okay, so yes, let's go back to where we were, if I can. Oh, that's the wrong file. Just a second. Intro pattern. Okay, so now this. All right, so the previous slide was that one, remember? So we talked about the various types of splines that people can use, and we said that there is a new vocabulary similar to the COVID situation. We have now a vocabulary which is analysis suitable splines, which did not exist before, because before one did not worry about being analysis suitable when people were talking about splines. And this is a useful thing to realize, is that the CAD world is the CAD world, and the analysis world is the analysis world. And these two worlds don't speak, at least didn't speak. And probably a really big impact of IGA is that it created discussions between the CAD world and the simulation world, which to some extent did not really exist before. And it's leading to some sort of merging of these two fields, which can only be good because it will make things more compact. In particular, if you've worked on topics which relate to dealing with CAD files, with all the formats, like step file, IGS file, and so on, you know how tedious it is to navigate through different types of CAD files which represent the geometry of anything. And so, if we could move away from that, that can only be beneficial. So I'm going to tell you a bit about what Nurbs are and what they are for, and what you can do with them, and also what the limitations are, and how you can hopefully go beyond these limitations. So now we're going to dive a little bit more into the details of what these things are. So first thing, you need to have a little bit of vocabulary. If you are familiar with finite elements, you may be a bit confused, because in finite elements, we have nodes. So these nodes are, for example, here, let's assume this is a finite element. Each node of the element would have a shape function associated with it. Typically, the shape function is of value 1 at the node and 0 at all the other nodes, such that you end up with this triangular shape above each node. So you would have a triangle above node 1, triangle above node 2, and so on. And just later on, I'll do a bit of writing about this so that you can understand it better. When you talk about Nurbs, you do not talk about nodes, but you talk about knots. And this is new vocabulary, which does not exist in finite elements. So you talk about knots, and these knots are not nodes. Okay? These knots define the shape functions that you actually use in there. In that case, they are
Nurbs, but they can also be B-Splines. And just afterwards, I'll try and give you a bit of details about this. So in order to understand the concept of Nurbs or B-Splines, the idea is that you have what are called control points. If you look to the right, you have this skeleton, this scaffold, which is drawn here, which is a polyline in red. And this polyline is controlling the geometry, but it is not the geometry. The geometry is the black line. And this black line is controlled by the position of the red squares. So if you move any of the red squares slightly, this is going to impose a change on the shape of the black curve. And that change is going to be governed by the Nurbs functions. And by changing the shape of the control polygon, which is the red set of lines, you can come up with almost arbitrary shapes. So for example, if you wanted to have a discontinuous function, you could create a discontinuous function. If you wanted to have a curve which is of order 3, you could have a curve of order 3. If you wanted to have more knots along this curve, you could actually do that too. So what is useful to think about is that you have what is known as a knot vector, and this is the parametric mesh. It's a bit similar, but not quite, to what you think about in finite elements when you think about the parent element coordinate system, but it's not the same thing. And then on the other hand, you have on the right hand side the control polygon and the the curve itself, which is defined by these knots. And you have a mapping between the two, and this mapping is done using the shape functions NA, which are functions of xi, and xi is the parametric coordinate. So now if you want to take any point on the curve, let's say here on the black curve, you are going to look at the position of that point x as a function of xi, the parametric mesh. And this is going to be a combination of the shape functions NA, which are these Nurbs, times some constants, which are the coordinates of the control points. So basically, at the end of the day, you end up with the position of any point on the curve that you want to model is a linear combination of shape functions NA of xi, and these functions come from the fact that you are using Nurbs. This is not more complicated than this. And in the 2D case, you would have not only one parameter, xi, but now you have two parameters, xi1 and xi2. And what you do is that you map this unit square to this shape using the similar mapping, but now in 2 dimensions. And you have this element, and this element here is akin to a parent element in finite elements. What you can see is that you can have, you will probably be confused here by these numbers, because you see 0, 0, 0, 0, then 1, 2, 3, and 4, 4, 4, 4. So why do we even have a repetition of different numbers? Because in finite elements, if you try to make an analogy, you would have here 0, 1, 2, 3, 4, and that would be the coordinates of nodes. But nodes are not knots. Knots can be repeated. So you can have multiple knots which are coinciding at one point. And that is super useful because it gives properties to the shape functions NA. So the shape functions NA that you have here, these shape functions will have different properties depending on the number of times you repeat the knots along this parametric line. For example, if you would like to have a line which is, if you would like to have a shape function which is interpolatory and therefore interpolates exactly the data at the end of the control polygon, or in that case of the parametric mesh, if you would like to have interpolatory properties at the ends of this interval, then you need to select the multiplicity such that it is related to the polynomial order of the approximation on this parametric mesh. And this is why here we have what's called an open knot vector, because the knots at the end of the interval are repeated the proper number of times depending on the polynomial order. Let's not go into the details right now. So basically what you can do is you can control the level of continuity along this, let's call it knot vector, in this parametric mesh. You can control the continuity. So if you wanted to, you could actually generate a control polygon, or a knot vector rather, such that you have here a jump, a discontinuity. So if you wanted a crack, for example, here, or if you wanted discontinuities, for example, for composites, then you could easily create a jump along one, at point one, a jump either in the function or a jump in the derivative simply by adding knots. So this knot here is at the moment value 1, and there is only one knot. If you wanted to create a discontinuity, you would increase the number of times this knot is repeated until you reach the polynomial order. And then, depending on the number of knots that you have, depending on the polynomial order, you would select that number of knots, and you would create a discontinuity. And so this is something that can be super useful, actually. So I'm going to afterwards show you a few examples on that, because it means that within one formulation, you can control the continuity of the solution. And this is one of the very useful points about Nurbs, is that you can control the continuity. Okay. So before I go back into a bit of more details about this, I just want to set the scene into a wider frame so that you can understand also when you read the papers. So here, this is a frog which is modeled on using Nurbs, and this is done on the Rhino 3D website. So here, this is the Nurbs mesh topology. So this is only a surface mesh here, not a volume. And the topology, as you see, I mean, it looks pretty much like a very regular mesh. And the idea is that you make a map between the regular mesh to this frog. And that creates the geometry that you're interested in, this map. So you basically wrap this thing such that you get this frog at the end. The problem is that you, in that case, need quite a large number of points. And in the case of T-splines, which is something invented more recently, you can locally refine such that you can, focus on areas where the curvature is higher and represent the frog in a, let's say, in an accurate way with fewer points. The second difficulty is that until now we talked about the surface of the frog, but let's imagine we want to talk about now the interior of the rabbit for various reasons. We would like to know what's going on inside. And if you look at the previous thing, what you see is that you have this square. This is a Cartesian mesh, right? It is squared in the x direction, in the y direction. Things are looking like cubes or squares. And this makes it non-trivial to create a mesh for such a shape. So because you need to parameterize the interior of this volume or shape for it to be mapped to a square with regular lines. So if you do local refinement, the problem is exactly the same. If you do local refinement, you will have refinement in the x direction and the y direction, because simply the shape functions that you have are the product of a function in the x direction and a product and the function in the y direction. So you multiply both together and you get shape functions that depend on x and y now. So it means that if you refine in the x direction, you also automatically will refine along the whole direction in the y direction, which is not necessarily what you wish, because you may want to only refine locally. And finally, you have this patch coupling difficulty. Okay, so I think what I'm going to try to do now is to connect using my tablet so that I can write a bit, which may mean that I need to, I don't know how that will work, so we will just have to check it. Okay, I'll mute myself temporarily so that
Okay, so I think, okay, can you hear me? Yeah, okay, so apparently this is working. I'm going to ask to share the screen here, if I can, which I hope. Okay, so now let's take okay, so it seems like you can see something. Yeah, it's working. Okay, good. Okay, so I think now we need to do a bit of I need a bit of writing, because otherwise it becomes really too difficult to follow. Okay, so first of all, we're going to talk a bit about what B-Splines and Nurbs. All right, so first of all, Nurbs are built from B-Splines. And so, of course, it's helpful to start from B-Splines so that you can understand a little better what's going on. Now, instead of, so in finite elements, so in FEM and in IGA, we will have a bit of different terminology. So in FEM, we're going to talk about elements. All right, so elements are these things in finite elements where, for example, you have, let's say, a few nodes, 1, 2, 3, 4, and 5. And now you're interested in looking at the shape functions for these nodes. So the shape function for node 1 would be looking like this, and we usually call it n1. If we draw the shape function for n2, the shape function will look like this, and it will look like 0 everywhere and 1 at node 2. And that is n2 and so on. You can deal with that for any of the elements, any of the nodes and any of the elements in the mesh. In IGA, what you have instead of elements, you have what are called patches rather than elements. So the parameter space in FEA, so that thing that we called finite elements. So if you remember, in finite element analysis, if you have a certain shape, you have in the shape some elements, okay, of course, triangles usually, but it could be something different. Then you map, so this has an arbitrary shape. This has an arbitrary shape, and you map it to a parent element coordinate system. And this parent element coordinate system looks like psi in the, let's say, psi direction, and it looks like, oopsie, eta in the other direction, right? And this is a reference element in the sense that the coordinates are like this, 0, 1, 1. So this is called the parent element. And this is called the physical element. This is the domain, omega discretized. And so you do a mapping, and you do a mapping because it's easier to integrate, to calculate everything into the psi eta coordinate system. So in right, okay, one more thing. Now let's assume that you have another element, so like that. Then you're going to have a different mapping, okay? Because each element has a different shape, okay? I would like to draw that properly. Each element has a different shape. So the mapping that maps this shape to the parent element will inevitably be different for each element, right? So the parent element is the same, but the mapping changes. So for B-splines or for Nurbs, what happens is that the mapping takes a bunch of these elements and maps that bunch of elements to a patch of multiple elements in the parameter space. That's what I was showing on the previous slide. So instead of having a one element by element mapping, you have now a patch which is mapped directly. So that each element in the physical space, which is this thing on the left-hand side here, each element in the physical space is somehow an image of a corresponding element in the parameter space, but the mapping is global to the patch.
not local to the element. So in a way, you can think of these patches as mappings. So sorry, as subdomains. Okay. So you know, you could think about that. Yeah, I think this is the way to think about that. So if you have, you know, many elements in finite elements, you will have many mappings, but in Nurbs, you will have only one mapping for a bunch of elements. See, so for example, if I draw the same picture as the one I just drew here for Nurbs, so you would have the domain, which is the same, and in there you would have a bunch of let's say elements that take certain shapes. So for example, here you would have these certain lines which have a certain shape. Okay, and that would be mapped as a whole to the parent coordinate system. So, and the parent coordinate system, in that case, as I showed before on the slides, you would have a xi direction, an eta direction, and you would have these lines which represent the iso xis and the iso etas, and this is what's called a patch. So you map the whole patch to the physical domain. This is the physical domain. And this is the patch. And you have now a mapping. And this mapping is effectively the B-Splines or the Nurbs or the T-Splines and so on. Okay. So that is really, really an important difference. And it will come up later. Okay, so now if that's clear, we can now move to the next point, which are not vectors. So what are not vectors? So not vectors are what I showed you just before. So usually the not vectors are written like this, which is a capital Xi, and they are written Xi1, Xi2, Xi n plus p plus 1. So what does that actually mean? So if you take this guy here, Xi I, this Xi I is that's a knot, right? So Xi I is a real number, and this is called the ith knot. Okay, I, which is here, I is called a knot index or knot index, if you would rather do that this way. There is another thing that we haven't defined, which is P. P is the polynomial order. And in Nurbs, in B-Splines, what is really cool is that polynomial order can be arbitrary. I mean, it can more or less be anything you like. And that is super nice because you have approximations which are extremely high order and they are extremely smooth as well. They can be arbitrarily smooth. It means C infinite. So this is really, really nice because that's not the case of most approximation functions that you have in, in standard Lagrange finite elements. And increasing the order, as we said at the beginning, these tetrahedral elements, which I was saying T3 to T6, so 6 noded elements, quadratic elements are not so easy to get by and generate and so on. Then here you don't have that difficulty. You will see that to raise the degree is very, very straightforward. So this is a big advantage of isogeometric analysis. If you need high order approximations and very smooth solutions, so maybe if you're in structural mechanics, you can think of cases where you need a smooth solution. So I can let you think about it for a few seconds. The basic point, okay, so yeah, for those of you who got the idea, congratulations. But for example, Kirchhoff love formulations, you know, for plates and shells, or Euler-Bernoulli beams. You know, these things will require to have a higher order continuity. If you do phase field modeling, very high order phase field models also, you know. So you have a lot of areas in mechanics and elsewhere you need high order approximations. When I say high order, I don't mean high order continuity of the solution, but well, yes, actually, I mean that the solution is of high order continuous across the patches and the elements, because in finite elements you have clear discontinuities across the elements in the derivative, which actually lead to errors, and that's how you can compute the error in finite elements, is by looking at the jumps between the elements. That gives you a good idea about how much the error is, if it's large, small, and where it is large, you can increase the mesh density, and when it's small, you can just leave it alone. Okay, so that's the that P is the polynomial order, and n is the number of basis functions that you use to construct the B-splines. So n is the number of basis functions that you use to construct a B-spline curve. Okay, so the knots, therefore, will create a partition of the domain into different, let's call them elements. And the element boundaries in the physical space are the images of the knots that of the knot lines, and the mapping is the B-spline. So that's what we showed here on the right-hand side between. So mapping is, for example, B-spline. Could be Nurbs, could be other splines, depending what you like to do. All right. So, and then there are different terminologies in the literature. So, you know, I'm not going to go into that much of detail, but this is yeah, this is the way it is. Okay. Then numerical quadrature is carried out on the patches at the knot span level. And so now, what are the properties of the B-splines? So what you will have is you will have different knot lines, and inside the knot lines, the continuity of the B-splines is going to be C infinite. So the B-splines are going to be C infinite inside an element. Okay. Which we can call knot spans as well. And many domains can be already quite complicated domains. Huh? Maybe represented by a single patch. And then what you need to do is you need to couple the patches together at the interface. Okay, so patches can be then glued together. And this is why, remember the leaky teapot. So this is why you could have leaky teapots, because let's assume that you have one patch that looks maybe like this, then you have another patch. And the approximation in the first patch can be maybe looking like that, of course. And the approximation in the second patch perhaps maybe looking like this. Because it could be that you use a higher order P. So let's say P2 is greater than P1. And here P1 is less than P2. And so, of course, at the interface, nothing will tell the two lines to be such that the approximation is constant, continuous. So that's why you end up with these ideas of the, leaky teapot, because here at the interface you could have jumps. It's good that teapots don't look like this normally. Okay. Because you may have discontinuities in the, on that side and that side, you may have completely different orders of shape functions, and it could just be completely different splines as well. All right, so that's it. So that's about what are knot vectors, okay, and the difference to finite elements. Okay, so now the knot vectors, you can think about them in different ways. Okay, so let's go back to our knot vectors. So what you can think about in terms of knot vectors, you can have them uniform. Okay, so the first type of knot vector is going to be a knot vector which is uniform. That means that all the knots are equally spaced. But of course, you could decide to have knot vectors where the knots are not uniformly distributed. Xi1, Xi2, Xi3, Xi4, and this is non-uniform, obviously. By the way, uniform and non-uniform here has nothing to do with the term non-uniform rational B-splines. That is, that's not necessarily the same thing. Okay, now what you can do is you can have repeated knots. So it could be that you have Xi0, 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 for example. And here Xi5, Xi5, Xi5. And maybe in the middle, you can decide to repeat another knot and call it Xi3 twice. Why not? And the multiplicity of these things have a very important impact on the continuity and the properties of the basis functions. Okay, so now a very important type of knot vector is called an open knot vector. And an open knot vector, let's say that we have a polynomial of order P approximation. So an open knot vector will be such that the first and last nodes, so Xi naught and Xi n, are repeated P plus 1 times. So this is p plus 1, p plus 1. This is an open knot vector, and this is important because typically in finite elements, why is it important? In finite elements, let's say that you don't want to do anything else than to interpolate things. So if you have a bunch of finite elements, or if you have one finite element for that matter, you're going to, well, what you do in finite elements is nothing else but simply, you take a curve and you want to interpolate that curve. So your goal is to interpolate this. And in finite elements, what you normally do is that you have linear approximations. But in finite elements, there are more than approximations because they happen to be interpolations. So this is also something that we need to know about in detail, because this comes up all the time. So if you want to interpolate something, you don't only want to approximate it, but you want to make sure that at the nodes, meaning at these white dots on the x-axis, the solution is exactly passing through the curve. So you're not approximating, but you're interpolating. So this is called interpolating. So when you do mesh-free shape functions, for example, you almost never interpolate. So your functions are almost always approximating functions. So, okay, so this was FEM. For example, Lagrange. So Lagrange polynomials. If you were to do something like mesh-free, based on moving least squares, what you would do is effectively the values that you would have, my apologies for this, the values you would have here would not be interpolatory. So you would have, maybe you would overshoot, undershoot, undershoot, overshoot, and so on, right? And then you would have some sort of curve that would be quite smooth, typically. It would be quite smooth and difficult to draw, but okay. So that would be mesh-free, and it is non-interpolating. And in the jargon that you will read in the literature, this is called the Kronecker delta. The Kronecker delta property. If I call the shape function associated with node 1, which is here n1, and if I call the shape function n2 and so on, and if I call these points x1 and that one x2 and that one x3, I should actually move that one to the right to be consistent with the others. So now if I do n1 of x1, the value is 1. The shape function, so those are shape functions. n1 of x1 is 1, and n1 of x2 is what? 0, right? Because I have this little add function. So it's 0 everywhere except at 1, where the value of n1 of x1 is 1. And everywhere else, it is 0. Okay, so that's that. So that is called the Kronecker delta property. Why? Because if you write ni in a general way of xj of any other point, this is delta ij, right? Which is 1 if I equals j, and 0 if I is not equal to j. And that is nothing else but the identity matrix, which you are very well aware of course. So that is the Kronecker delta property, and mesh-free, for example, moving least squares, so that sort of gibberish thing I've written here is moving least squares. You can check Belichko IJNME 1994, 1995, and 1996. and in the element-free Galerkin method. If you want to know more about that, take a look also at our review paper, and everything is described very clearly there. So you are not interpolating. I'm spending a lot of time on that because it's important. So if you're not interpolating, it means that the solution you get out of your solution process, you will get a U vector, like some unknown vector you're solving for, but that unknown vector locally at each node will not be equal to the physical value of the unknown. So for example, if you're looking for displacement, you'll get a bunch of values in the displacement vector, but those will have nothing to do with the values of displacement at the nodes. So it means that the solution at the node is not equal to the nodal value at the node. It's not a problem, but just you need to know it, because if you just look at the raw values out of your solution, then you will get stuff which doesn't mean anything physically. And obviously, you need to know about that before. So why is that important for B-splines? Because if you have a p-order polynomial, as we have here, this p-order polynomial is going to govern the number of times you need to repeat the end knots in order to be interpolatory. So for the B-spline to interpolate the solution at the end, then you will need to have p+1 repetitions of this, okay? So you will be only interpolatory at the end. So that is to be thought about, okay? So if you have a knot vector which is open, okay, so let's assume this is the direction. Let's assume that those are the knots. And let's just say that for the sake of argument, p equals 2. Then you will have to repeat knot 0 3 times, which is p+1. And 0, 1, 2, 3, 4, you will need to repeat knot 4 3 times. p+1 equals 3 times. And then your solution is interpolatory at the end of the interval, not everywhere. So that means, again, if we use the same colors, if I can find them as before, and let's assume that we want to interpolate this function. So let's say that this is the thingy I'm interested in. It looks like that. This is the so-called, let's call that the exact solution, right? We don't know it, but it doesn't matter. Let's say this is what we want to interpolate, or we want to approximate to be approximated. So that can be the shape of a composite panel. It could be the solution to a time series, like say a number of COVID cases at the University of Luxembourg, or whatever it is. But then in that case, the direction would be time. It would not be space anymore. All right, so now we want to approximate this thing, and well, we want it to be interpolatory. So if we go for the case where we have a repeated knot vector, repeated knot at 0 and 4, we will be interpolatory, which means that we will exactly nail the solution at the end of the interval, right? So it means that in between we don't know, right? So this psi1, psi2, psi3 are such that we do not know what's going to happen in between. But we know that we have p equals 3, so we cannot do arbitrary things. But all we know is that we will, something will look like maybe like this. Who knows? So at the knots, you see, we will not be except, oh my goodness, amazing. I managed to create a particular case where it is interpolatory, also in between. So yeah, just consider it's not, right? So here we are not interpolatory, here we are not interpolatory, here we are not interpolatory. So those are only approximating, but not interpolating, because we are not equal to the value of the function we want to approximate. Right, so that's cool. okay, probably the example I just drew is not super precise, but at least you get the gist. Okay, so open knot vectors are in the CAD field the standard, and if we have in one dimension at least open knot vectors, which repeat the knot at the end of the interval p plus 1 times, then we are interpolatory. So that is perfect. In multiple dimensions, they will be interpolatory at the corners. So if we take a patch like so, then we will have interpolatory behavior at the corners. So again, the way to think about it is that if we try to approximate a function here that looks, let's imagine, like this. So we try to approximate this function. It might do something like this, I don't know. And on that edge, it might do something like that. And we try to approximate this on that edge. It might do something like this. And on that edge, maybe something like that. So that is the function we want to interpolate over the square. If we have open knot vectors, then we will indeed interpolate at the ends. So maybe we will be having a shape of the interpolation which looks somewhat like that, for example. And in between, we won't be interpolating. So we may end up like this, for example, if I manage to draw it. And here we might end up with a different shape, but at least at the ends of the intervals, we will be interpolatory, okay? But in between, we don't know, right? So only the end knots are interpolatory. So that is important because it means in between, we don't know exactly what is going on. Because in finite elements, that is not the case, because in finite elements, everything is always interpolatory, so you don't have this problem. Okay, so now let's look, once we have the knot vector, we can draw and we can basis functions. We can define the basis functions. So what are basis functions? So let's say that we have a knot vector at hand, and we would like to construct the B-splines. So what are B-splines? So the idea in B-splines and also in Nurbs, by the way, is that you can construct these things in a recursive way. So you have a recursion formula, which starts from p equals 0, and then you will increase p, and as you increase p, you will get the higher order function from the p equals 0 case. So let's assume that we want to create B-splines basis function. And it's useful to do that at least once, because then you see how things look like, and it allows you to really, really understand better what you are dealing with in the simulations later. So the first thing is, you remember we had a knot vector, right? So the knot vector was, you can call it psi I. So psi 0, psi 1, and so on. And psi, I think we had n plus, n plus p. In fact, let's start with psi 1 instead of psi 0. Let's start with psi 1 and psi n plus p plus 1. Okay, so this is the knot vector. And we want to use that knot vector in order to create a B-spline. Now we're going to create B-splines by patches, as we said. Okay, so we're going to look at the patch, which is composed of the knot vector xi I less than or equal to xi less than or equal to xi I plus 1. So you can imagine you have a line, and you have this this knot vector, which has who knows how many knots, it doesn't matter, but here you have xi I plus 1, and then you pick a xi, which is somewhere in between on the closed interval. Okay, fine. Now what do we want to do? Well, we first start with p equals 0. So p is equal to 0 means constant. So what does it mean, piecewise constant? It means that your approximation, if this is 1, you know, each interval here is part of the parametric space, then you will have a piecewise constant approximation. Okay, that's not very rich, but that's what you have to start with to construct the B-splines. Okay, so now it means in each of these little segments, you're now going to have a constant. And the question is, how do we deal with generating the higher order functions? Okay, so first of all, we're going to write n I comma 0. So this is here p equals 0. That is the number of the interval. Okay, because you have here xi I. You rewrite that properly. So xi I, right? So this is the same I as this one. This p is equal to 0 is the polynomial order. It's the fact that this thing is a constant. All right, constants. And then what we're trying to figure out by that is, how do we write it? So first of all, that function, it's a shape function. It's a function of xi, which is the parametric coordinate that you have here, this xi. And what can we say about it? Well, it's very simple. It's the characteristic function of the thing, of the interval, which is 1 if xi is in xi I plus 1, and 0 if, well, otherwise. Okay, so this is nothing else but the characteristic function of the integral. Sorry, of the interval. Right, so now what do we do if we have p greater than 0? So p equals 1, 2, 3. Well, in that case, you have a recursion formula, and the recursion formula looks like this. Ni, so same thing for the same interval, comma p. So p now is the polynomial order, which is greater than 0 strictly. So 1, 2, 3, and so on. Evaluated at xi. What is xi? Well, xi is the value along the xi axis, the parametric axis. Well, the definition of that thing is what? So it's xi minus xi I divided by what? By xi I plus p, polynomial order. So it's like a translation, minus xi I. And then we multiply that by what? Well, by the, we said it's a recursion formula. So by ni p minus 1 of xi. And now we need an extra term, which is what? Okay, so now it's going to be, so xi minus xi I plus p minus xi I is essentially, you know, xi minus xi I is this. So it's a change of coordinate system, basically. Okay, and then the second part is the complement of that. So psi I plus p plus 1 minus psi divided by psi I plus p plus 1 minus psi I plus 1. Okay, and that is multiplied by n of I plus 1 p minus 1 of psi. And so that guy you don't obviously need to know by heart, but it's called the Cox-de Boer recursion formula. And the references are 1971 and 1972, X, Cox, and de Boer. So de Boer is that one, and Cox is that one. And now, if we are trying to see how that would look in reality, so this would be, for example, you try to, okay, maybe I should, well, okay, let's do it this way. Let's assume that now you want to have to draw these things, then this is going to be n1, 0. For the second, you're going to end up with n2, 0, you know, and so on. You can keep drawing. All these things are, so this is going to be n3, 0, and so on. Okay, now if you, so this is p, this is p0. Then now if you want to draw the same thing for p1, what you are going to get is the following thing. You're going to get the first okay, the first function will be, this one will be n1, 1, p equals 1. The second function will be this triangle. So n2, 1. If you draw the third one, you start to get the idea. That is n3, 1, and so on and so forth. And that's going to be for order 1. Now, if you want to draw that for order 2, of course, as soon as we start going into order 2, things are harder to draw. So probably it will look ugly. But as you can see already, actually, before we go to P2, let's already note something which is quite cool, is that you see here, each function acts only on this little edge, right? So you see function 1 acts on this. Okay, maybe I should actually give it a different color so at least it makes sense. So this is function 1. Now, if you want to look at function 2, it acts only on this. You know, it's 0 everywhere else. That's what I mean by acts on. And this is also here non-zero, but 0 everywhere else. Now let's look at the first order case. So this is P0, right? First order case, look at the span of the function. Already it's now taking 2 elements. And now if you take the span of the second function, it's obviously also taking 2 elements. And the span of the third function is taking 3 elements. So it means now that the support, so this is terminology that you probably know from finite elements, the support of the shape functions, the B-splines, is increasing in size when you increase p. So it means the higher p is, the larger the support of the function is. The support means the set of size for which n is different from 0. Such that n of psi is greater than 0. Okay, the support of n. So the support of n increases as you increase p. So of course you can guess, and I didn't say it, but the value here is 1 and the value here is 1. So now I'm going to draw that a bit for that case, right? So you have here 0, 1, 2, 3, 4, 5, and normally that should be enough. And now we're going to draw the shape functions associated with node 1, but for P2. You see? So now let's see what happens. So if we draw the shape function for node 1, okay, for P2. So what you will see, actually, maybe you don't, it's difficult to just make up, but I can tell you that if you draw it, you will see that the function takes value 0 and has slope 0 here, value 0 and slope 0 here as well. Then it will be maximum somewhere between 1 and 2, which is not evident at all. And it will not have value of 1 at all at the top. You know? So I will draw it as best I can. Yeah, something like that. So that's going to be, it looks a bit like a Gaussian, and n1, 2. And if you do that, well, first of all, what do you realize? Is that now n1, 2 has a support which takes 3 points, right? 3 nodes. And so as you can see, p equals 2, 3 nodes, p equals 1, 2 nodes, p equals 0, 1 node. Okay, so that's already clear. And now we can draw it for the second one as well as we can manage. And so maybe first of all, I'll draw something horizontal here. Okay, and I'll draw the second one. So the second one will be 0 and tangent at 1. It will be 0 and tangent at 4, and in between it will look like this short sort of bell-shaped curve. And if you look at the span, again, the span is larger than in the 2D, than in the P2 case. And similarly, you can draw it for the third one. Okay, so what did we learn here? We learned, oops, that doesn't seem right at all. 2, 3, 4, yes, because I didn't, the maximum happened too much to the right. So, okay. Thanks for your patience with that. All right, so now this is the third one, n3, 2, and the second one was n2, 2. That's the shape function. And this is a uniform knot vector. Again, the knot vector in all cases was psi equals 0, 1, 2, 3, 4, and so on. So we just selected the knots to be equally spaced. Okay, so what can we say about these guys? So there are several things that can be said and that are that I would say quite useful, interesting, and helpful when you do IGA. So as you can see, the shapes are all the same. They are all identical, but they are shifted relative to each other. But in a quadratic finite element, the shape of the element depends where you are, if you are at the end of an interval or in the middle of an interval. So you don't have the same shapes in case of a quadratic finite element using Lagrange shape functions. So that's already a different thing. You have here an homogeneous pattern, and if you increase the higher the degree, what you will see is that the span, which means the support of these, will be larger and larger, and they will overlap more and more, because you can also see, that's something that you saw in the P2 case, that there is an overlapping now between the functions. You know, they are not mutually exclusive. So in the P0 case, there is no overlap. Only at the ends of the intervals do the shape functions overlap. In the P1 case, you can already see that there is overlap here and overlap here. And in the P2 case, you can see that there is overlap between the 0 and the first, the 0 and the third. So that is, sorry, the first and the second, 1 and 2. This is overlapping between 1 and 3. And you also have overlap between 2 and 3, and so on. So you see that you have more and more overlapping of the shape functions. And I'm sure that if you think for a few seconds, you can deduce what that will lead to when you assemble the stiffness matrix. So I'll let you think for a few seconds so that you can think a bit. Okay, so for those of you who were able to find it, congratulations. Otherwise, you can sit back and enjoy the show. But basically the point is that you will have a larger bandwidth for these overlapping shape functions, because the fact that they overlap means that the first node is going to talk to the second and also to the third, which means that in the matrix that you end up with, you will have the first column will not be empty, the second neither, and the third neither. So you have let's say a bandwidth of, let's call it 3. Of course, it's not 3, depends on the problem, but so it will be larger. And this is something that is going to be inevitable in isogeometric analysis, something to keep in mind. It's not a big deal. It just means that the solution schemes based on iterative solvers, for example, will converge a bit slower. That if you use, Gauss elimination, direct solvers, you will need more memory, and so on and so forth. So it's not a big deal. It's just something you need to know. Okay. What else is important about these functions? The other thing that's really important is that they form a partition of unity. So that means that if you take the sum of those functions from 1 to n of capital N I, P of xi, this is identically equal to 1. So this is trivial in the first case, because you see here, this is 1, simple, N2 is 1, and 3 is 1. So if you sum all those functions at any point, you will see 1. Why? Because if you take psi here, you take the sum, the only non-zero value is n1, and it is equal to 1, so that's fine. If you take now psi here, and you look at the value, you get 1 again, and so on. So you will always get 1 because the functions are not overlapping. So the sum is always equal to only one of the functions because all the others are 0, except in their own, you know, support. Now, if you take the second case, you get exactly what you see from Lagrange polynomial, because basically, you know that these are the Lagrange polynomials. They are exactly equal to the Lagrange polynomials of order 1. So they coincide. And now what you can see is that if you take any point, so if you take it here, of course, you have another function that you don't see here, right? So let's take any point. Let's say here, and you look at the sum. So n1 is equal to whatever it is equal to, and the other part is equal to that. And as you can see, this little part here, that's here, is equal to this little part here. So if you sum the two, you get 1. I mean, you can write it as analytically, it's much better, but okay, you get it. And here is the same. So except that now you have 3 functions in certain areas that contribute to the partition of unity. For example, here, if you zoomed in that area and you try to find out what is the sum of the 3 functions, you would have 3 functions that are non-zero at a point, right? So you would have this part, and this part, which is not 0. Okay. So that would mean that you need to sum the actual 3 functions, and they happen to sum to 1. I mean, you can prove it using the recursion formula, but I don't think that's really the point here. Because why is it even useful to have a partition of unity? So again, this takes probably a 30-hour course on partition of unity method, but our book will come out soon with Sundar anyway, so you will be able to read that. It's going to be published with Wiley in this year. And we talk about what is partition of unity, why it's useful, and so on. And I think basically you just need to remember that it's useful because you can reproduce constant fields like constants. You can reproduce linear fields, quadratic fields, and because of enrichment, you can reproduce any field. And that is thanks to Ivo Babushka and his idea of partition of unity enrichment around 1994, 5, 6. That time where he said that it is enough to multiply this partition of unity by any function, and you will be able to reproduce that function precisely, exactly everywhere where you introduce it. That means, and you will see the applications later during the course, that you can enrich the partition of unity, enrich the partition of unity method associated with IGA using arbitrary functions like discontinuities or singularities, jumps. And at some point, I will show you the comparison between an enriched and not enriched isogeometric formulation for debonding of composites. And you will see this is work done by Yuanvin Fu. And this is really cool because it shows you how IGA can help you deal with discontinuities either with enrichment or without enrichment. And I think this is an extremely nice idea that Fu had. All right, we also see that they form a partition of unity. We also see that for all xi, we have NIP of xi strictly positive, actually positive or 0 if you count the end of the intervals. It means that here I actually didn't draw that absolutely rigorously properly because I should have also told you that at these ends n1 is 0, okay, and at these ends, you know, n2 is also 0, and so on, right? So you understand that. All right, so now we know that these functions are non-negative, so this is very nice because we can use mass lumping if you do dynamics. Okay, and then in the mass matrix M, you will have M1 blah 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 M n, and all the mi's will be strictly positive, which is very nice because it really avoids having problems of stability. Okay, very useful. And also it's actually very useful for convergence also of the schemes, non-negativity. Okay, now the third thing is that it's related to continuity. Okay, so that is called positivity, something you really need in times of COVID. And this is called partition of unity, already said, and this now is called continuity. So if you take a P order function, so B-spline, that implies that you have P minus 1 continuous derivatives, okay? But not continuous anywhere across the element boundaries. So that means that is really, really nice because it means that contrary to finite elements, where across the element boundaries you do not, unless you use Hermite polynomials or something else of the similar ilk, you will never have continuity across the elements. I mean, that's not something you have of the gradients, let's say. You have only continuity at the nodes of the solution, but you don't have continuity of the gradients. That's why you have all these jumps. That's why the elements that are like tetrahedral elements that I talked to you about, you remember at the beginning, for the motivation, I talked to you about these, tetrahedral elements, and I told you about locking, I told you about how stiff they were, and so on. So that stiffness, that locking, and so on is due to the fact that you have jumps between the element spaces. You have epsilon equals constant inside the element. So if you draw the solution across a one-dimensional field, for example, what you will see is that the solution will be constant, constant for the strains, will be constant, 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 constant. And you see here these jumps between an element and another element, 1, 2, 3, 4, 5. You see these jumps, element 6. And these jumps, in fact, define how accurate the solution is, because the solution that you're trying to figure out, and this is something that's really interesting that I cannot talk about because of the fact that we have only 3.5 days to do that, but I'll be happy to do it another time, is linked to error estimates. So this is the error, right? So if you assume that the solution that you want to find out is smooth, the more jumps you have, let's say this is epsilon exact, right? The gray one, or whatever color it is. I'm colorblind, so bear with me. So that thing, if you have a jump here, it intuitively will mean that the solution is incorrect, right? Because you have a big jump, but the solution is supposed to be continuous. So how can you have a big jump if the exact solution is continuous? It means that your solution does not reproduce the exact solution precisely, because otherwise you wouldn't have jumps. So conclusion, pretty simple, is that the more jumps you have, the worse the error is. And this is, so those of you who are interested, you can look at Zinkiewicz and Zhu. It's about 1970s in IGA, and what they talk about there is how to use what is called the SPR, which is a superconvergence patch recovery technique, which allows you to actually compute how important these jumps are in order to compute the error in the domain. So this is something quite useful to think about. And if you have p-1 continuous derivatives across the element boundaries, it means that in IGA, instead of having these things which are jumpy everywhere, you will have a solution which will be much less jumpy, unless, of course, you use p equals 0 or p equals 1, because then you degenerate to the same case. So, but if you use higher order p's, then your solution, instead of looking like a jump, it would look like something quite smooth, right? Even across element boundaries, and which means that you will have a lower error, because if you look at the difference between the dashed curve and the exact curve, then you will see that you have much more continuity. So that's the idea of IGA. It creates continuity where the other methods are relatively discontinuous compared to it. Okay. So that has huge importance later. And this is really distinctive to IGA. However, if you think about it, you can think of, so C mesh free. So I cannot resist the idea to tell you to check that out, because continuity was also one of the, let's say, guiding principles of mesh-free methods when it was invented in the, let's say, 1990s with element-free Galerkin, because people were using their what is called moving least squares approximations or radial basis function approximations, and many others that were extremely smooth, and that, in fact, infinitely smooth. And therefore, somehow there is some similarity between the advantages and the drawbacks, incidentally, of IGA and mesh-free. And this is such one. So mesh-free and IGA share the similar feature that they are both able to give you a high-order continuity across the domains, especially at the domain boundaries. And this is very interesting and very useful. Okay, and finally, this is something that we already said. So the support of NP is p+1 knot spans. So that's what we said, when we went here and we saw, right, so that, this third thing here has a knot span of 1, 2, 3, 4. So 3 knot spans because 4 knots, right? So just so that the vocabulary is completely transparent, this is a knot span. This is here psi4, psi5, okay? And so you have 4 knots and you have 3 knot spans. And the idea is that if you have p equals 2, then you have 3 knot spans. If you have p equals 10, you have 11 knot spans. And so the overlap of these things is very important. And of course, this is going to increase the bandwidth. So okay. Let's say in general, this may increase the bandwidth. Okay, so well, actually, this question of bandwidth is quite complicated because it depends on how many nodes or knots have a non-zero value associated to any other knots. And so this is not always the case that the bandwidth will be increased, but at least intuitively speaking, this is what comes to mind. Okay, so I'll tell you more about this tomorrow, I think, because I believe that at 1 we're supposed to stop. Is that true? Yes.
Yes, that's correct.
Katerina nodding. So so what I will do, if it's okay with you, is tomorrow I'll resume. In the meantime, I would really appreciate any comment, feedback, questions, hints, whatever, so that I can decide this afternoon what I talk about tomorrow. So I know, of course, in the first 2 hours what I have in mind, but I can always, because I'm just going to continue on this train of thought. But in the next hours, I can still decide what to talk about. So it would be nice to know what you guys are up to and what you would like to tackle, what you would not like to tackle. If the style is okay, if it's too slow, if it's too fast. If you'd like more examples, less examples, more things about theory and less about the literature, or more about literature and less about theory, a particular paper you've read that you'd like to go over, but try to be fast, because I still don't have, I have less than 24 hours to look at it. But if you have some ideas, I'm really happy to take a look at that and try to help. So if that's all, then I guess we reconvene tomorrow morning at 9 in the same way. Very impressed to see that things have worked, actually. Thank you very much, Catherine, and also Arnaud Mazier, who is, I think, somewhere here listening, for helping, because it's always difficult to predict whether things will work or not. So I'm very glad that it did. And thank you to everybody who attended and for your participation. And yeah, really, please don't hesitate to tell me a bit, yeah, how you'd like me to take it on from there.
So I just want to say a few words. Thanks, Stéphane, for the nice lecture today. Thank you to all the participants. Please feel free to send the questions you have to me or to Stéphane directly via email. You can also post on the YouTube link. We will search for that during the rest of the day, and see you tomorrow at 9.
Thank you very much. How do I do this now?
Okay. Have a nice day. Bye.
You too.